Hello, everybody, and welcome to our second day of OARC 36. I'm Ulrich, and I am in the PC for OARC, and we're really happy to have you here today. And with that, we dive right into our first speaker. Geoff Huston is talking about measurements of the NSEC validation with RSA 4096. Please, Geoff, start sharing your slides and
off we go. Thank you very much, and good morning all. It's good to be here. This is a relatively quick talk about DNSSEC, and in particular the RSA crypto algorithm, and looking at the extended key sizes with RSA. The issue is, of course, that RSA is not what you'd call a dense algorithm. In order to get a high security level, you actually need a relatively long key length. And as you can see on the slide, what's the security level? Well, a security level of n means that you need to perform 2 to the n operations in order to solve the problem posed by the cryptographic text. So a security level of 140 means you need to have 2 to the 140th operations for an RSA 4096 encoded piece of text. The problem is not really the fact that computers are getting faster, it's the real issue of quantum computers. And although we really don't know how quickly and how big, the theoretical work proceeds. Using a mere 20 million qubit quantum computer, if we're ever going to make something that massive, evidently 2048-bit RSA could be solved in 8 hours. But that's a huge amount of horsepower. Now, you might be concerned about this. You might want to protect your data for longer than 8 hours, and you might believe that quantum computers are going to happen really, really quickly. They might. I have no idea. You might also have an issue with ECDSA because it's a slightly lower level of quantum resistance. So, well, maybe you should try RSA with 4096-bit keys. Yeah? Well, let's have a look. Certainly, RSA 4096 is big. The private key is, of course, massive, 3,300 bytes. But the things that impact the DNS is actually the public key and the signature. And again, as you see there, they're both pretty large. The private key up to a kilobit, the signature 744 bits. So, you know, you're paying a penalty for that degree. What about performance? It's very slow to sign on my computer. I was signing 500,000 entries and I used a number of algorithms. And as you see there, RSA 4096 is kind of a dog. Validation times, however, and I was validating 50,000 responses using a very small internet, in other words, across my room. And the validation times, I think, is dominated by all the rest of the DNS activity. So they're largely similar. But the issue is the response sizes. And in particular for RSA 4096, it's the DNS key response size. For those of you with, I don't know, medium memories, you might remember October last year with DNS Flag Day 2020 proposed a maximum DNS payload unfragmented of 1,232 octets. If you're using RSA 4096, you've just bumped over the top of that by 13 octets, whereas ECDSA P256, of course, comes in easily at 347. So is that a problem? Because in this point, you're going to be delivering truncated answers and doing a flip into TCP. We actually had a bigger look at this whole issue of offered eDNS 0 buffer sizes, and this measurement was taken in September of this year. And 17% of users, not resolvers, users, query via recursive resolvers that use a UDP buffer size of less than 1245 octets. So this larger key will have a time impact for around 17% of users, as far as we can tell, give or take a bit, because the user might be using more than one resolver. But you notice there the jump points 1232, 1400, 1472, and 4096 appear to be the 4 major UDP buffer sizes at the moment in DNS. Our test rig, I've been through this many times before. It's an ad. We do around 12 million samples a day. We sort folk into 2 classes. Either they're validating, in which case we see all the right queries, they fetch a validly signed object, and they do not fetch an invalidly signed object because the DNS is basically not answering it. And there's a mixed validating class where they do all the right queries, but when they get back a DNS validation failure, a serve fail from their recursive resolver, they just go and ask another resolver that doesn't validate, and they get the answer and go and fetch the invalidly signed. About 27% of users validate, around 10% of users are mixed validators. So let's have a look at this using two algorithms, RSA 1024 versus RSA 4096. Validating, 29.7% of users worldwide for 1024, and a very small change, 0.3% of a change downward for RSA 4096, and a slight uptick in mixed. So this was across 84 million samples over a 7-day period. What we actually found was that not 17% of users, but 26, which is a little bit higher, had a smaller UDP buffer size and were given a truncated response. Most of them followed up using TCP. 2.5% didn't. They just didn't do the TCP. And of those, most of them, 4/5, said, oh, look, this is just getting too silly. I'm going to go use a different resolver that had a larger UDP buffer size. All good, because everyone provisions with more than one recursive, it all works. But a very small amount, 0.5%, failed that DNS resolution. They just couldn't find a way out because the TCP follow-up was not working for them. Is 0.5% inside the experimental error range or a significant number? I tend to think it falls towards experimental error. But I also think this test is a little bit fake. I don't know, and I think folk like Ed Lewis and Victor Duchovny spend a lot more time looking at this than I do. But there is a lot of a fashion out there to separate your keys and use a separate zone signing key and key signing key. But what that does mean is your DNS key record now gets larger. And it gets a lot larger when you're doing a key roll because old signs you, and you're going to then have 3 of these keys in your DNS key record for a while. So let's have a look at those responses. Immediately you're jumping up 1200, 1700 to 2200. And the validation outcomes are now all showing that stress. When we go above 1500, we tend to lose just under 2% of users there, because what goes on is more and more folk are now trying to flip to TCP and they're not making it. But what's curious is a much bigger jump from 1700 to 2400. I have no idea. It shouldn't happen like that. What's going on? Well, are people lying about the UDP buffer size? And when we send 2400, it goes, oh my God, I didn't mean it. Don't send that to me. Is the 2400 a path MTU mismatch in the frag? I don't think so. Is there some other security policy? Receive a buffer limit? I'm like, are your front-end firewalls going, look, I'm sorry, no one sends that big a DNS. I'm just going to throw out the packet because I'm a firewall and I do such things. I have no idea, but it is odd. It could be a TCP problem, but again, I just don't understand why. It could be a balked DNS implementation or load distribution front-end size filters, which might be more like it, where the load distributor is going, people don't send that kind of size packet. I'm just going to give up because, no. So failure to reconnect with TCP also rises, and this is failure to complete the TCP transaction. But again, it seems odd. TCP doesn't know in advance that I'm trying to jam down 2,200 bytes, but I get a much higher failure rate nevertheless. Either TCP is really prescient, or there's more going on in the DNS infrastructure than a simple model of a simple resolver would indicate, with a lot more front-end and processing, which is actually size sensitive. And that's kind of curious. So where is it a problem? Well, the winner today is Portugal. 68% of users validate with RSA 1024. And when I use 2 keys in RSA 4096, that drops by a phenomenal 28%. You can read the rest too, but that's just by country. Yeah, okay. Here are a few ISPs where the recursive resolver inside that ISP is really having problem. P4U-MTS in Poland is a massive drop. EACOM in Ireland, again, massive. But you can read that as much as anyone else. I do have larger lists on request. But, you know, yes, this does seem to be an issue with some ISP resolvers just not handling it.
Geoff, you've got 5 minutes for your Q&A.
Yeah, I'm just coming into the end now. Does RSA 4096 have a future? Nah. Maybe we should be looking at something else, because I think it's also unwarranted. You only need to keep a secret for the lifetime of your keys in DNSSEC. As long as you roll your keys frequently, then you don't need to have long security lifetimes. Now, RSA 1024 can't do 10 years, that's true, but it can certainly do a couple of months, even 6 months. And for DNSSEC, that's long enough. So all this idea that I need to get NIST level 20-year security for DNSSEC is actually misdirection. It isn't valid for this application. The other thing is with quantum computing, you also have to understand a different concept, dimly understood, called quantum resilience. RSA is thought to be more quantum resilient than ECDSA, even though ECDSA is much more compact. But if you're worried about that, geez, I would have thought there are more things to worry about than that. Anyway, we have enough time for some questions now, so I'll hand it back. Thank you very much.
Thank you, Geoff. That was a really interesting talk. And please, everybody, write your questions in the Q&A pod. And if you want to speak up, raise your hand and we give you the microphone. And oh, we have a comment here from Greg Choles, and it says, comment, not a question. Large DNS responses may be broken because DNS network and security people are not working together to make sure it works every time. Experience shows that network people tend to use ping to validate PMTU, and DNS works most of the time. So it's okay, right?
Yeah, I know what you're saying, but the big threshold is 1500 octets, which is the typical MTU of the public internet. And my question is, why, when we move from 1700, which is big, and it's over 1500, to 2200, which is still just big, it's more than 1500. So the real thing is, so what? They should be the same, but they're not. And it's that issue that kind of gets me, because I don't understand why there's differentiation between those two values. That's the bit that I don't understand. There's something in the middle here. But my guess is, from the lack of comment, nobody here is either willing to own up or understands what's in the middle of the mess that we call a resolver in today's rather complex DNS infrastructure. This mess of load balancing and front ends and, you know, pre-processing of queries and pre-caching probably causes a huge amount of hidden side effects with larger packets that are just not well handled. And we only stress it out when we actually push the response size up into that space that is not normal. So, you know, ECDSA, everyone, stay on the safe side.
Yes. So I would like to remind everybody, please answer the poll that is up, should be up on your screen right now. And we have another question here from Peter Thomassen. In your AdNet study, how did you distinguish failed validation from other error conditions?
Failed validation, I can actually see, because we use a particular form of query name where I can see both DNS key and DS key queries because they're uniquely named. Caching won't work. So I'm actually looking for the DS, DNS key, and quad A queries down at that sort of bottom two labels to actually understand that someone is trying to validate. If they're not trying to validate, they won't ask for DNS key and DS key, and DS records. So that's why I know they're trying. And I actually give them two parallel problems to solve. One is validly signed, one is invalidly signed. I should see the DS and DNS key for both names, but I should never see a fetch of the one that's invalidly signed, because that will always deliver serve fail. So that's the way I do the distinguishing. Yes, there's a certain amount of experimental error in this because the link between DNS and web fetching has a certain drop rate, but that's the best you can do in this kind of server-based experiment where I can't instrument the client.
Okay, and then we have a question from Latour. Not awake yet, but it's anyone thinking of writing a paper to state the quantum resilience of DNS, rotating keys monthly is good enough for the next couple of years at least?
Well, that's the kind of conclusion. And I must admit, I keep on hearing from some of the security folk, oh, you can't use 1024, RSA 1024 in DNSSEC. It's just not secure, says NIST. And I'm sort of going, you're looking for 20-year protection. But when you're rolling your keys every 6 months or 1 year, that's irrelevant because this key only has, if you will, a lifetime of vulnerability when the parent is busy saying this is valid. Because once the parent key rolls, all that old keying information doesn't matter anymore. DNSSEC doesn't encrypt. It merely protects authenticity. And so this whole argument, which is around Dane, that, oh, we can't use DNSSEC with RSA 1024 is actually just specious, ignorant nonsense. Understand the nature of the way DNSSEC works and understand the reason why we're using cryptography will give you much better guidance on key sizes. You don't need to protect the cryptography. You're protecting authenticity for the duration of the key lifetime. They're different concepts.
Okay. We have another question. Jarle Frederik Greipsland asked, would it be useful to try and pinpoint exactly what UDP package sizes causes steps in the successful validation rate? e.e. Fine-tune the key size in steps of 1 byte.
Wow. These are difficult experiments to set up. Joao Damas is on this call, has worked with me on this time. He will attest. These are incredibly hard to set up. They take us some months to get tuned and accurate to run for even a couple of weeks stably. There's a lot of work that goes on behind it. The amount of work to try and get 100 million or 80 million queries for each 1 byte step, I'm sorry, there's just not enough time, in the day. It just can't do that. So, no, I'm sorry, just not a feasible approach. But you're welcome to try, please, be my guest.
Okay, and then we have a question from Magnus Sandberg, and he asked, I think Darwin will sort this out. When DNS uses more TCP and modern transport methods, failing firewalls or DSL modems will be replaced. I agree that we as a community do as much as we can. Darwin will do the rest for us.
Unfortunately, you might remember Petr Špaček's OARC contribution 1 or 2 OARCs ago, where he suggested that even simple TCP adds a penalty where the throughput drops by 30%. The whole issue is that the DNS is an economic nightmare. It is a failed market. Almost 70% of users use their ISP's resolver, and from the ISP's perspective, the DNS is a cost center, not a revenue raiser. There is no economic interest in DNS over TCP, Magnus. So unfortunately, while it sounds great, the incentive to use it out there in people spending money land is zero. We are stuck with UDP. We've cemented it and bolted it down, which is really depressing. But quite frankly, ISPs don't care. You don't choose your ISP because the gold-plated wonderful version of the DNS resolver they're running for you. God, no. So they run crap because you'll still be their customer and you'll still pay them money. So no, DNS over TCP is a distraction. Unfortunately, in Geekland, it might sound great, but it just ain't going to happen. It's going to take forever to get there, if we get there at all. Well, that's my personal opinion anyway. One of many.
Good. Thank you, Geoff. I think with that, we have come to the last question, and we're right on time. So
it's a pleasure. Thank you very much.
Thank you. And so we go right on to our next speaker. James Richards is talking about an analysis of DNSSEC signed domains appearing within a large web crawls dataset. James, please start sharing your slides. Yes, I can see your slides.
Brilliant. Can you hear me okay?
And I can hear you. Good. Please
Excellent.
Go ahead.
So hello, everybody. My name is James Richards. I work as a researcher at Nominet here in the UK. I normally do DNS threat intelligence for Nominet's customers, but I'm talking today about a personal project I've been working on for a couple of months to study DNSSEC deployment within the common crawl dataset. So what is it that I'm studying here? So many DNSSEC deployment studies focus on lists of domains, such as those occurring in a TLD, perhaps. I often see the results range, somewhere in the low figures, 5 to 10%, maybe DNSSEC deployment. However, if we consider the web, users are rarely delivered all the website content from one single domain name. Often multiple domains are utilized. So if we have a look here on the right, this is our corporate website, nominet.uk. But there's actually quite a lot of domains used to deliver content from other places, images or scripts or analytics, etc. So the question I've been asking myself is, how do the DNSSEC prevalence statistics change when you include all of these other domains? And how interesting, what interesting methods could we use to quantify it, I guess. So separately, I came across the Common Crawl dataset a while back, and I've been meaning to make use of it in an interesting fashion. It's a free to access dataset hosted in S3, and it's got data going back quite a long time, many years. I did my study in October, November of this year using the July-August Common Crawl data. And it comes in a few different formats. So the raw web crawl data comes in a walk format. And this is essentially the raw web scrape data from their crawler. But I've been working with the WAT data, which is basically computed metadata in JSON format. So what you can see there on the right is that each resource is basically associated with a JSON element. So you can see there's a style tag and some CSS that would be used in the web page to load, whatever formatting you have on that style tag from that resource. So we can extract domain names from this quite easily and do some interesting work. I found it quite an interesting and useful data set to work with because it's been put together really, really nicely. So what I'm trying to do here is analyze domains that are used to deliver content to a website. This is obviously going to require some judgment, and we could probably debate what is and isn't content, but I've kind of gone down the line of thinking that a hyperlink is an example of a domain that appears within a web page, but it doesn't necessarily get resolved at the load time with intent to deliver content like an image, for instance. Whereas in comparison, a domain that's used to load images is itself a source of content for that web page that's being rendered. So I've done my best to categorize these domains, and I'd actually be quite interested in hearing from the audience if anybody else has tried to do this and had success with it. I'm going to define two types of domain for this presentation. The primary domain, which I'm going to say that's what users type into their search bar at the top. So in this instance, nominet.uk. I'm going to define content domains as being those which are used to load stuff that we see, whether that be images, scripts, all manner of odd and wonderful things that web developers put in their websites. Basically things that are used to actually create the page. So how have I done this? Well, there are lots of different types of HTML tag, and I didn't have time to learn about all of them, unfortunately, as much as I'd have liked to, because being a DNS person and not a web developer, I wanted to find a way to scale this out quickly. So I've been using the Mozilla MDN elements library. So essentially, this allows you to categorize each tag into a broad category. And then I've been using those categories to extract what I believe is related to content. So, scripts, multimedia, that type of thing. I'm thinking in this way, I can more easily determine which domains I should include in my study. But there is a lot of odd stuff, as I'm sure you'd expect, working with internet scraped data. There's a lot of esoteric tags for kind of niche website content. I found some augmented reality frames, which I've never seen before, which were pretty cool. There's a lot of websites with a high number of unique domains. There's a whole variety of reasons this is the case, but they do exist out there. They popped out quite quickly when I was doing the analysis. We see domains that don't resolve. And obviously we see a difference sometimes between what's been crawled from an automated machine versus what would be rendered from a real browser with a real pair of human eyeballs on it. So these are just challenges we have to live with for the study, but I've tried to make some assumptions that remove that variability. So the data set I worked with comprised of 72,000 files, nearly 22 terabytes of data. So it is a big data set, and there's a lot of these discrete data sets of that size on this platform, which is good to work with. I processed them in batches of 48 over a period of a few weeks. I began by iterating through each file and selecting those domains below an ICANN suffix and at the root directory of a website. So there's a lot of websites that are presented at a subdomain level or on a specific path, maybe like a specific blog article, for instance. I didn't want to double count, so I'm hoping that this kind of normalization step I'm doing at 2 and 3 allows me to compare apples with apples. For each website that passed those tests, I looked up the primary domain with the DNSSEC bit set, see if there was a signature present. I then analyzed all the tags and the hyperlinks within the content of the website itself and looked those up with the DNSSEC bit set as well. I then threw away any of the content that wasn't required, so any of those kind of inline text elements that wouldn't be associated with content. And then I assumed anything that came off of a relative reference was from the primary domain. So you can see there /picture would have been an example of coming off the primary domain as a relative reference. So this provided me a data set as follows. So you basically have rows of data that are for unique tag and content domain pairs. So we've got information such as the primary domain, whether it's signed with DNSSEC or not, which class of element that HTML tag came from, what domain name was being used to load that element, and then some DNSSEC information about that content domain as well. So you can imagine the data set I derived was basically millions of rows for lots of different websites that look a bit like this. I threw away any rows of data for domains that didn't resolve or had NX domain or serve fail. It didn't make a lot of sense to me to include those, but I suppose we could probably debate whether they should have been included. But this is kind of what I was working with to derive a lot of my results. So here are some high-level statistics. So in total, I analyzed 13.5 million domains across over 1,000 TLDs. A majority of the data was in COM, org, net, and CCTLDs. There was a small amount in GTLDs. Within each of these websites, in total, I found 16 million content domains. So 16 million domains used to deliver images or scripts, similar things to that. 7.7% of the websites of the primary domains were signed. This kind of aligns with other studies I've seen, so I thought that was a good result because it hopefully means I'm on the right line here. Of those domains that were signed, we see a split in the algorithm between 13 and 8, which again I think is largely a good thing. I think those are the most popular algorithms that I'm familiar with. So hopefully that kind of validates some of the collection techniques I was using here were working as I expected. The graph on the right here is quite interesting. It shows how many content domains there were per website, or per primary domain, I guess. So the majority of the websites we looked at had 5 or less content domains. So 5 or less domains used to load images or scripts, for instance. There were a very small number of domains that had thousands of sources, and they're quite fun to go and look at why they're there, but they were few and far between. By far, the majority of the websites had a kind of smallish number of domains. And this is the answer I really wanted to get to in my study. So if we split the results into categories, we can see how it breaks down. So 78.2% of the websites had no DNSSEC at all. So not on the primary domain and not in any of the content. 14.1% of the websites weren't signed, but had at least one piece of signed content. If we move over to the top right, 6.1% of the websites were signed at a primary domain level, but had at least one piece of content that wasn't signed. And then the kind of the perfect example down in the bottom right there, where the website itself was signed and all of the content that was being loaded, 1.6% of websites were in that category. So we've got quite different numbers on the page here. It could be anything from 21.8%, which is if there's some DNSSEC present anywhere, all the way down to 1.6% if it's completely DNSSEC secure. And obviously there's that middle number there, 7.7%, if we just look at the list of websites that we scanned. So really, this gives us quite a lot of different perspectives on how we could measure it or what's most meaningful to people. And I found it interesting that the number of websites that DNSSEC impacts on in some way is 3 times higher than the rate of signed primary domains would necessarily give you from just evaluating a list of TLDs, for instance. So it might affect how we think about risk or other features of the protocol. So how much of a website was signed? So this could be measured in lots of different ways, right? How many kilobytes of data were delivered to users with signed domains, or how many unique domains or screen real estate maybe. But these are probably topics for a future study. What I've done here is just present the data that I've discussed on previous slides. For those unsigned websites, so unsigned primary domains that have some DNSSEC in them, it's normally not very much DNSSEC. So you can see there almost 100% of the data in the blue category is inhabiting the lowest bin on the graph there. So if you've signed your website, if you're using an unsigned website domain and you've got one or two bits of content in there, that's where you'll be in that bottom bin. If we look at websites that are signed at the primary domain, you're much more likely to get more content signed from other DNSSEC sources, or indeed from the primary domain itself. So you can see here on the right with the orange chart, quite a lot of the websites that were signed actually are fully signed, with all of the content being delivered from DNSSEC source domains. So really getting that primary domain signed so that all of your relative references are delivered from DNSSEC secure sources is quite important. So in this figure, I've broken down the signed rate per Mozilla MDN category. So you can see how varied the different categories are, with some types of content quite unlikely to be delivered from DNSSEC sources and other types of content much more likely to be. Note that the graph starts at 80%, so we're still talking at quite small numbers here. I've not analysed this view of the data in lots of detail. There's quite a lot going on here, but I've been through and pulled out some anecdotes about different domains within each category. So if we look on the right-hand side, we can see obsolete and deprecated elements. Now, I would have imagined that obsolete web page components wouldn't have been signed. Maybe they're kind of old-fashioned and weren't being looked after, but actually they're the most likely to have a DNSSEC signature out of all of them. I think this is occurring because there's various features like parked pages. So there's one TLD in particular which has quite a lot of parked pages, and within their template they have a frame with a signed domain inside to deliver content with inside that frame. And the frame object was removed from HTML5, which is why it's considered obsolete. So I think that has quite a disproportionate impact on that category, because there's obviously a lot of those parked pages that were being scanned. Similarly, if we look at scripts, there are a couple of CDNs that are very popular that are used to deliver scripts to website templates that people use. And I think disproportionately that's had a positive effect on the impact of script delivery in the websites that we've scanned. So if we look conversely over at the left-hand side, you can see that embedded content is the least represented in the DNSSEC chart here. I've been through some of these domains in this category, and a lot of them look like kind of trackers or analytics systems that might tell you what users are visiting your website. And a lot of those domains don't look like they're signed, which again disproportionately affects this category because those domains are seen all over the internet, and therefore you're going to get quite a lot of that content affecting this statistical outcome. So it's a kind of similar story with the algorithms. So we can break down the algorithms per category because we collected that information. It's a bit less varied than the previous graph, but again, we do see some differences. I suspect that, again, this is driven by a lot of those commonly seen domains that are deployed across multiple websites in kind of template fashion. But nonetheless, we do see quite a lot of algorithm 8 and 13, which is kind of similar to the results we saw earlier, which again, I think is expected because these are the most popular domains, popular signing algorithms that I'm aware of. So on the topic of common domains, it's not a surprise that we see the same domain used across multiple websites. You know, it makes a lot of sense that developers would do that. They use common supply chains and common CDNs, allows them to scale their websites quickly. Within the data set, the top 10 common domains are seen within 68% of websites. So that's quite a high number. It's much higher than I actually expected. And of those top 10 domains, only one of them is actually signed. So these are mostly populous.
James, you've got 5 minutes till your Q&A.
Brilliant, thank you. Most of these are kind of popular CDNs, analytics, and other services. I'm not going to comment on whether these should be signed or not. You know, each company has its own business drivers or their own reasons for deploying domains as they see fit, depending on their infrastructure. So I've obfuscated the domains because I'm not really interested in individual cases. I'm more interested in the kind of trend and the behavior. But you can see there that what this view of the data is basically telling me is that as you move from the left image, where the primary domain isn't signed, to the right image, where all of the domains are signed and all of the content is signed as well, this is going to be heavily influenced by, I think, these commonly seen domains. It may be a struggle for some website owners to actually reach that right-hand side if they're relying on a lot of these common tools. They may not necessarily have the choice of DNSSEC signed domains to provide this content if there's a lot of inertia in the industry to use certain tools or certain classes of application. So something slightly different that I didn't use the Common Crawl dataset for was redirect analysis. So I was kind of interested in how many websites redirect from signed to unsigned domains. So for instance, I could navigate to a website and I might receive a 301 redirect to another domain. The question I wanted to answer was how often are those redirects to unsigned domains? So I did a rudimentary study using the Python requests library. So I basically asked it to follow all of the redirects in a chain for all of the signed domains that were crawled. I then took that list of redirects and checked whether all of them were signed, and then extracted those where there was a break in the chain of redirects between DNS signed domains. I was only able to analyze 75% of the data because, to be honest, I ran out of time. I would have liked to have got to 100%, but I'm hoping 75% gives us a good idea. I found that less than 0.1% of the signed websites redirected to unsigned domains, which is much better than I expected. I don't know why I was expecting it to be worse, but I thought this might be a kind of a gotcha, but it turns out not to be. It's actually quite good statistically. I think there's probably more work to do here around redirects and the interaction between that and DNSSEC signed domains, particularly content domains. So some of the statistics I presented earlier were talking about prevalence of certain types of content within websites. I didn't obviously do the redirect analysis on those, so maybe we should do that next time around as well. So in conclusion, what is it that we actually want to measure? So if we're concerned about any DNSSEC at all being present within a website, the deployment statistics could be as high as 21.8%. Now that's a much, much higher number than 7.7%, which is just the raw list of domains from the TLDs that we measured. But obviously this includes any DNSSEC signed content, no matter how small or insignificant. However, if we wanted to be purist and sign every domain for every piece of content that's loaded on my web page, it could be as low as 1.58%. Now that's obviously much, much less than 7.7%. So that's maybe a bit of an unhappy or worrying number. Neither of these numbers are necessarily right or wrong, but I would be interested in the opinions of the audience as to which number is more meaningful to you. Do you care more about the number on the left or do you care more about the number on the right? I'm sort of in two minds about it, really. The positive news is that I saw websites rarely redirecting from signed to unsigned domains, which is good. But unsurprisingly, a small number of popular domains were seen in lots of different websites, and only one of those was signed. So I've been kind of thinking since I completed some of these statistics, like to what extent does a website owner actually have control over their DNSSEC posture? So if you're a large enterprise that's running your own CDN or hosting all of the infrastructure you use off of domains that you can control, you could possibly get to 100% if you're driven to do that, if it's appropriate, and if you want to for your business model. If you're a smaller outfit, or if you're building your own personal websites, you might rely on common supply chains to do that. Certainly I do when I build websites. I rely on all those tools that are out there. I might not necessarily have a choice of using DNSSEC signed domains for all of those tools. If we did the study again, there's lots that we could improve, perhaps use headless browsers, maybe scan from user endpoints. I would couple the DNS and web data collection much more closely together. There was a bit of a lag between those two because of how I was doing it. And I'd probably build a more robust HTML tag dictionary just to more accurately measure some of this stuff. But I think the results I got certainly answered my initial question, and I was quite happy with that. So I'd be happy to answer any questions you have.
Okay, thank you, James. Well, a very large study. It must have taken some time, actually.
Yes, I think I had a 48-core machine running in AWS for about 3.5 weeks or so.
Yes, so we already have some questions here and maybe comments. We see here we have a question from Hazel Smith. If I understood correctly, and the poll's coming. So please, everybody, answer the polls. And I read the question here. If I understand correctly, this data set is based on approximately 13 million domains. How do these uptake percentages compare to those for popular domains? Unsure what the most relevant metric would be here. Is Alexa top 500 still relevant?
That is a really good question. I was considering comparing these statistics to something like Tranco, you're right, or OpenDNS or Alexa. I didn't get around to it, so I don't have the numbers off the top of my head. But normally when people do DNSSEC deployment studies, I expect to see something in the sort of 5 to 10% or 5 to 15% range. So I wouldn't be surprised if those numbers came out similar or maybe slightly lower. But yeah, that's a question we should look at.
And then we have a comment from Magnus Sandberg. Comment on redirects. I guess a lot of redirects are within the same organization. If you sign one domain, you sign all your domains.
Yeah, absolutely. And I think one of the things I enjoyed about this study is that I went in with some assumptions and they were challenged quite heavily by the results that I saw. So I think the comment that I put on that slide about there being more work to do around the redirects and the interaction, I think you're completely right. That definitely needs more detailed examination. Certainly, sometimes when you've got a complicated situation, it deserves a little bit more, fine-grained analysis. So that might be something I can do on the next round if I get a chance to do it again.
Okay, and people, we're closing the Q&A line, and but if you have more questions, write them in the chat. I think James will answer them. And with that, we go to Pieter Lexis. He has a question. Please, Pieter, you can ask your question.
Yeah, thank you, James, for this. It's pretty cool. So you mentioned both the redirects and that you looked for RR6 on the A record. Did you also check if the DNSSEC chain was valid if there were CNAMEs involved?
Yeah, so that's a good question. So I did because I wanted to analyze a large amount of data in a small amount of time, I basically just looked up with the DNSSEC bit set on an A record. So there are situations, you're right, where CNAMEs would compress down into one response for that type of query, and I didn't analyze that in detail. I just accepted that single response back from the resolver. So yeah, there's definitely some expansion we could do on the results there, but I think I wanted to just take an initial stab at this data set and kind of see what I got out, and these kind of suggestions are the kind of things I'd like to review next time round if I get a chance to do it again.
Right. So you actually looked at the RR-SIG and not if the AD bit was set on from the recursor to you.
Yes, yeah. So when I got a response back, I iterated through all the answers and checked whether an A record was present and whether an RR-SIG record was present.
All right. Thanks.
Okay, and then we have another question from Latour. It would be interesting to see how IPv6 is doing in that framework.
Yes, yeah. Yeah, so I didn't scan for quad A records. So again, that's obviously another blind spot, I guess. I think my assumption here was that the A record would be a good proxy for maybe some of these results, but you're right, more results would be quite interesting to compare between the two. That might be something I can have a look at next time around.
Okay, and then we have a question from Peter Hessler. And did you do any analysis on how many partially signed pages would go fully signed if the 10 most popular content providers were signed?
No, so I had grand plans for doing all sorts of differential analysis on that data set, but it turned out to be quite large. And when you're doing lots and lots of comparisons between data sets, it basically, I kind of ran out of compute resource at that point. So I think some of the more interesting questions, I think we'd need to design some kind of analysis framework for, because I think certainly when you're loading 13 million domains and all of their content references into an object, it does become quite challenging. So the answer is no, but it is something I really wanted to do, and hopefully I'll get the opportunity to do it if we can design some way of achieving it in a compute engine that makes sense.
Good, and then we come to the last question. Arsen Stasik asks, how many subdomains signed if the parent domain is signed?
How many subdomains are signed? So the study I've done is based on the domain name we saw within the web page. So of course, DNSSEC might be, and probably is present in the vast majority of these domains at a parent level. Certainly all the TLDs are signed, well, nearly all the TLDs are signed. So DNSSEC will play a role in all of those different statistical outcomes, but I was only analyzing the actual domain as it was, with subdomain or not, as it was seen within the web page. So yeah, I don't have any statistics on the interaction with the parent zone, I guess, at this point.
Okay, and with that, I say thank you, James. Certainly a very interesting study. And with that, we have come to our first break. We reconvene at 11 UTC and hope to see you all back. Good, and with that, off to coffee. Hello, everybody. Welcome back. I hope you used your break well, and we dive right in with Pieter Thomassen and the status update on authenticated bootstrapping of DNSSEC delegations. Please, Pieter, share your slides.
Yes. Hello, everybody. Can you see my slides?
Yes, we can see your slides and we can hear you. Please go ahead, Pieter.
Good. Hi, I'm Petr Špaček from DSEC and Secure Systems Engineering. I'm going to give a short status update on our internet draft for authenticated bootstrapping of DNSSEC delegations. I guess many of you have heard about it, so I'll keep it a bit more concise than in previous presentations. So for those who don't know what it is yet, here's an overview. If you enable DNSSEC for a delegation, you have to convey your DS records to the parent, and it's usually not very clear how to do that. There's various ways of doing it, often involving the registrant, and that we think is one reason for the low deployment rate of DNSSEC, which is around 5–6% on the DS securing side. So the draft that we have provides in-band authentication for bootstrapping a secure delegation to publish a DS record for the first time. And if you have that authentication, you can automate the whole process and hopefully increase the prevalence of DNSSEC delegations. The proposal is based on CDS and CDNS key records at the child apex. So for example, if you have example.com, you can publish next to the SOA record in the example.com zone CDS records and CDNS key records, which indicate to the parent how to construct a DS record and put in the .com zone. And the process we're proposing is for the parent to verify that the contents of those CDS and CDNS key records haven't been tampered with. The verification happens through a chain of trust to the DNS operator that has to be pre-existing. We use the operator's name server domains for that, which are known from the NS record set. And so what's required is that you use DNSSEC for the name server domains. Yeah, so this is something we've proposed to the DNSOP working group of the ITF, and let's see how it goes. So here's a very quick overview how it works. I said initially that you need to have this pre-established chain of trust to do the signaling to the parent. So you need the signaling mechanism. It has two general properties. It allows publishing arbitrary information about zones the DNS operator is authoritative for. We will use this for DNSSEC bootstrapping, but the mechanism could be used for something else in the future. And it's authenticated and can be done on a per zone basis. It works by using the namespace under each name server host name. So for example, one of our name servers is ns1.dsec.io. And we are proposing to reserve the _ds_off label, and underneath that, you would have the signaling stuff going on. As I said before, it requires DNSSEC. And yeah, so you can make announcements over the DNS, on the DNS domains that you host by encoding those announcements in subdomains of the DSOF label. So here's how to do it specifically for DNSSEC bootstrapping. We start with the CDS and CDNS key records at the apex of the target zone that is supposed to be, that is in the process of being secured. And then we just co-publish these records identically using the signaling mechanism under the namespace that I explained above. So you would have example.com._ds-off.ns1.dsec.io. And the interesting point here is that these records would be signed with the DNSSEC keys of the name server zone and not of the target zone. So you can validate that stuff with the pre-existing chain of trust to the name server domain. Yeah, so once the parent does that, they can check whether everything is fine, stuff validates, check this against all the different name server host names that are provided in the name server record set. And if all is fine, transfer trust can be transferred to the target domain. That's how we call it. So you could take these CDS records and CDNS keys, construct a DS record set from that and publish it at the parent. One important thing not to forget is to clean up the records when you're done. To keep the bootstrapping zones small. Yeah, here's a quick illustration for those who like pictures more. So let's say we have the root zone, which is secure, and the net and com TLDs, which are also secure. And we have a provider with provider.net zone and DNS1.provider.net name server host name. Let's assume all of this has DNSSEC. And now the customer comes and registers example.com. It will usually not be secure. But the DNS provider may add the CDS and CDNS key records to the customer zone, which is what is usually done already according to, well, not usually, but there's an RFC for it. And we're proposing to co-publish these records under the name server host name to use the DNSSEC chain of trust on the left here to validate what's in the child zone. So then the registry and registrar can come, look at the child zone, validate that against the records in the name server provider's zone, and secure the customer's delegation at the parent. So we use an established chain of trust on the left to take a detour, and we get an authenticated immediate way for publishing DS records at the parent that is resilient against on-wire attackers, active on-wire attackers. Some technical considerations. So there's no collision with the original use of CDS or CDNS key records because those are at the apex only, and we're proposing to add a new use case for these records on non-apex names in the subdomains of the _DSOF domain. We also, yeah, so this is what we also propose to put this label in between, to have some kind of technical separation between the name server host name itself and the bootstrapping stuff that's going on underneath. This enables delegating the signaling data to a separate zone. And so if you think about the technical aspects of how to run this operationally, having this separation removes the risk of accidentally modifying the name server's IP records, for example, because you don't even have to touch the name server zone to do bootstrapping stuff. It reduces the churn on the name server zone. It allows splitting of DNS operations, as I said before. So you could do online signing with a different key. You could even synthesize the answers. And if you use NSEC walks, so if you use NSEC instead of NSEC3 in the bootstrapping zone, you could have a parent walk the to-do list, so to speak. So for example, .com could come, look at com._ds-off and do an NSEC walk and find that there is example.com to be bootstrapped. Similarly, if you do allow a public zone transfers, the parent could come and retrieve this subsection of the bootstrapping tree, if that is a separate zone, and perform the different bootstrapping tasks that are to be done. Some numbers on the bootstrapability in the Tranco top million. So we investigated the top million in October. We had about 2.3% failure rate, timeouts and all that. We didn't spend much time on improving that. We found that 5 or 6% of zones are secure and or signed. So secure is if you actually have the validation path, and signed is if you don't have DS records but are R6. So this is just a cross check, and we found that about 25% of those top million domains do already have name servers which are secure themselves, or the domains are secure. So those are already suitable for performing the bootstrapping mechanism. And if we take those and we also require that the domain hosted on it is not yet secure, then one could use those name servers to do the signaling and to secure the domain that they host. This is the case for about 22 or 23% of domains in the top million. So that would mean that if this is employed universally, which of course it wouldn't be, but maybe significantly, then up to around 200,000 domains could be secured with it right now without anyone having to change the name server DNSSEC configurations. In the backup slides, if you want to look later, there is a breakdown by DNS operator and all that. We can skip that now. There are some limitations. So some edge cases cannot be accommodated by the design. So for example, if you consider the domain foo.bar.net._dsauth, then bar.net would be the signaling name for the bar.net delegation, and foo.bar.net would be the signaling name for that one. And so now if you had a zone cut at bar.net._dsauth for some reason, if you had that, then there would be a semantic collision because the CDS record there would also be at the apex of this bar.net._dsauth delegation. So you couldn't use it at the same time for signaling for bar.net. So that's not a huge restriction. It's just worth pointing out. The model also doesn't work when the target name is excessively long or has too many labels, because we append something to the target name. So it could be possible to run into the length restrictions. It's also unlikely to happen, but it's also a restriction technically. And also it doesn't work to bootstrap domains which are in bailiwick, because if you have a domain that's in bailiwick and you need to bootstrap it, that means that you don't have the validation path yet. Otherwise you wouldn't be trying to bootstrap it. And if you don't have the validation path yet, however, you can't do this kind of authentication that we're proposing.
Peter, you have 5 minutes until your Q&A.
Thank you. I'm actually almost done. So here's the status and outlook. We presented this at the IETF 112 meeting and gathered some valuable feedback. Based on that, yesterday we uploaded a new version of the draft to the IETF data tracker in case anyone wants to look. The most significant changes are that earlier, the signaling names, which were encoded in the subdomains of _dsauth, had a component that was hashed, which gives some edge case advantages, but was considered to be too complex. So the protocol was simplified. And now we only prepend the verbatim name of the target domain to this bootstrapping domain name. So that's a simplification. It's now much easier to, for example, query these things using dig without having to use some hashing tooling or something. The intermediate level _dsauth was also called _boot previously, and we changed that because it was considered to be too generic. The _dsauth is also just a proposal, which I think is well fitting. But if other people have opinions on it, it's not set in stone. We also clarified the importance of cleaning up bootstrapping records, and we added a section on the limitations I just explained. We're looking forward to having more discussion on this, which is why we're presenting it here and not only at the IETF. If anyone is interested in giving us feedback, that would be highly welcome. And otherwise, we're looking for DNS operators and registries or registrars who are interested in exploring and deploying this protocol experimentally. We think the protocol is kind of taking shape and coming more close to its final form. And I think the adoption by the IETF DNS Ops working group may happen in the next few weeks. I think a call was announced to be started in a few weeks or something. So we're getting closer to implementation phase and would be highly interested in operators and registries and registrars who would be interested in working on this from the publication and from the processing side. Yeah, thank you for your attention. I'm ready to take your questions, if there's any questions.
Thank you, Peter. Well, I have been following your work, so I abstain from commenting. But please, people, write your questions in the Q&A pod, and or raise your hand if you want to ask your questions yourself. And please vote in the polls that should be up on your screen right now. And Well, in the meantime, Pieter, have you done any implementation of your own?
Yes, so we run this at DSEC. So you can go to, well, like these underscore names, and then you can perform an NSEC walk, for example, for our own DNSSEC bootstrapping, but it is not yet adapted to the new label. So we still use the underscore boot label, not the underscore DNS-OARC label, and still we also have the hashing in the owner name of the bootstrapping stuff. So we will update this in the next days to accommodate what's in the draft since yesterday. And yeah, so that's what we currently have. There's also a tool for performing this NSEC walk and extracting these information from the bootstrapping zones and output a list of DS records that one could use to put in the parent. So this would be a tool a parent could run to see what is missing for securing the delegations and just have all the validation done by the tooling. I know that obviously people would be running their own tooling and integrate it into their own CDS scanners and all that stuff, but we wanted to give a proof of concept with that. Yeah, so that's it as far as our implementation is concerned. And I also know that probably most questions on this have been asked before, so I'm not going to be angry if there's no questions.
Well, we have a question here. Okay. Magnus Sandberg is asking, how broken is EPP or the communications via the registrars? You have to have some trusted communication either via your registrar or your NS provider.
So let me see if I understand the question correctly. So these bootstrapping records have to be processed by some parental agent, so to speak, and that could be the registry or it could be the registrar. I think for the generic top-level domains or the non-CCTLDs, it would always be the registrar because the registry is not supposed to have any relationship with the domain owner and the DNS operator. So let's assume we have .Berlin or whatever, and the registrar, let's say, for example, GoDaddy, is going to scan whether the child domain has this bootstrapping stuff configured. Then they would be fetching it and validating it. And then later, they would have to pass on the DS configuration via EPP to the registry. Now, the question is how broken that is. I'm not sure if this is exactly the question. But so earlier, there were some concerns by people, for example, if the registry would parse this, then they would be updating the DS record set in the parent and the registrar wouldn't know about it. So maybe if they would have their own database at the registrar level, that could be out of sync with the registry. So that is true. In that sense, one could say it's broken, but that also applies to any CDS update generally, not just for bootstrapping. So this is something to be sorted out between registry and registrar. And I don't think it has specifically to do with EPP. Now, if we go back to the case where the registrar does the parsing and passes things on to the registry via EPP, I'm not an expert on that, but I would think there is some TLS there or some other transport encryption and authentication. So it's not clear to me exactly what's meant with the question, how far that's broken.
Well, Magnus has a follow-up and he says, okay, if you have a good contact with your registrar and the EPP with the registry works, you don't need this.
Yes, that is true. But the thing is that usually most people, especially domain owners, like companies registering some random domain name, they don't even know they have a registrar, right? They have some web hosting company that does everything in the background. And ideally, it would be nice if the registrant wouldn't have to do anything to have DNSSEC enabled, if the DNS operator could just decide that by themselves. So our take is that the setup to enable DNSSEC currently is too complicated. Does that answer the question?
And as an employee of a registry, I can agree with you. Well, I think we have answered all the questions. Thank you, Pieter.
Yep, thanks.
And with that, we come to our next speaker, another Pieter Lexis. And he is going to talk about the proxy protocol. Please, Pieter, share your slides. Yes, I can see your slides.
All right, thank you. So welcome to the Pieter show indeed. I'm Pieter Lexis. Peter van Dijk is co-presenting here with me because he did most of the technical implementation. So if you have any implementation questions, then he can probably answer them better than I can. So we'll be discussing the proxy v2 protocol for use in DNS. And first of all, what is the problem that we are trying to solve? Many DNS setups can be or are fronted by load balancers and proxies for various reasons, be it firewalling, be it dropping packets early, etc., or maybe putting just the cache very close to the end user. Unfortunately, many of the backend servers that are fronted by these load balancers and proxies, they require the actual client IP address for ACLs, views, other purposes like filtering or policies. And many proxies don't actually want to do expensive parsing of DNS packets because, well, they either can't or it is just very CPU intensive to parse the packet in your load balancer and then again on the other side. It is also quite possible that a backend might want to know about the transport being used, including port numbers, for instance, for CGNet purposes, or knowing that something was requested over a secure channel. And there are some solutions for this. One of them is abusing eDNS client subnet. One of them is the xproxied4 or XPF record that can be added to the additional section. And then there's, of course, private and bespoke eDNS options that you put in the DNS packet from the load balancer to the backend. And these have several drawbacks. One of the drawbacks of using, of course, client subnet is that you're squatting on an existing option, which is usually a terrible idea. It also requires the load balancer to parse the DNS packet in flight and modifying it. Maybe even breaking TSIG, so you would have to strip it out at the backend again, and there is so the backend also has to be modified. There's also no way to then pass eDNS client subnet through your proxy because the proxy has to add its own eDNS client subnet to the auth in the backend. There's no port information in there, and there's also no transport protocol information, of course, in eDNS client subnet. Then the drawbacks of XPF and other options. XPF had the information about ports, had the information about transport mechanisms. However, the draft expired at the IETF, and there seems to be no real momentum behind it anymore. And of course, it also requires parsing and modifying DNS packets in flight, and also requires some special handling to not break TSIG. And then there's private eDNS options or bespoke eDNS options. And this requires changes to all the software in the chain. And of course, it is not a standard or well documented. And of course, it can be very hard to debug with any of the standard tools that exist. So this is why for PowerDNS, DNSViz, we have implemented the proxy v2 protocol, and we hope, of course, other implementers will do this as well. This is a binary protocol that prefixes the data that is being proxied. And it only lives between the proxy and the backend. The backend does not even respond with prefixed data. It can pass IPv4, IPv6 addresses, ports, and protocol like TCP and UDP. It is extensible using any tag length value fields, for instance, to pass the DOH path or to pass TLS information from the client. Many load balancers already support this protocol. And of course, it goes very well together with eDNS client subnet in the original packet, because there is no modification of DNS packets by the intermediate proxy. Where are exactly these headers placed? These are the two most implemented options. So the client will send a query that comes to the load balancer or proxy. Then the proxy will prepend the proxy header and send the original query to the backend server, which then responds without any proxy information to the load balancer, and then the load balancer passes on that response to the client. You could also have direct server return. We have not implemented this because we like having our proxy to keep statistics, but there it's exactly the same. Client sends a query, proxy sends the query off to the backend, prepending the proxy header, and then the response immediately goes back to the client. There are many implementations of the proxy v2 protocol already. Many load balancers, also open source like HAProxy, support it. Actually, this protocol originated at HAProxy, although they do TCP only, whereas we also do UDP, of course. There's a bunch of web servers like Nginx and Apache that supported also only TCP. We've implemented this in DNSDist 1.5 for outgoing. DNSDist 1.6 also supports proxy protocol incoming, so you could have a chain of proxies there. PowerDNS Authoritative Server 4.6 and Recursor 4.4 support inbound proxy protocol as well, and use it to populate their structures of the original addresses. Bind9 and Unbound have this on the roadmap. I believe Unbound wants to do the first half of next year for a proper implementation, and Bind9, so ISC is working on it, but don't have anything promised. And not DNS, the Auth has an experimental patch as well. I'll now go into some description of the proxy protocol. It's like I said, it's relatively simple. There is a header that identifies this traffic as being proxied. It then is followed by the proxied address, the source address, destination address, including all the ports. Then you can set any arbitrary data as tag length value, and then just the original data follows after that. The header is prefixed for every query over UDP. And when you do a TCP connection to the backend, the header is sent only once at the beginning of the TCP connection. This data is valid for the entire TCP transaction, even if there are multiple queries over that connection. There's no header in the reply, so there is no information from the backend going back to the proxy. And as I said, there is no TCP reuse to the backend if you have different clients. The header is rather simple. It contains a 12-byte signature. And if you would send this to a regular DNS server, it would end up in a form error response because it does not parse properly as a DNS header. Then there is some information about the protocol that was used. So this is set to the number 2 because this is proxy protocol v2, and then the command. There's only 2 commands. There is proxy and there is local. Local means I don't actually have proxied data following, but I'm doing some local command. We use this, for instance, for the times that we do health checks. Then there's the protocol family and socket family, and then a length field. I said it's relatively simple. The proxied address is just a union. This is how it looks. You have all the source information and destination information depending on the protocol that is in use. And yeah, you can even do things over Unix sockets if you really want to. The tag length values, again, you have a type field, you have 2 length fields, and then the total value. And this can be used to send more information to the backend if that would be required. And of course, the backend supports this because unknown types will be ignored. Within the protocol, there are 12 types already defined, like the SNI that was used, mostly for TLS. Of course, the ALPN information, some client certificate information, etc., etc. And within DNSDist, we support adding your own tag length value fields onto the proxy header, and on the recursor end in the scripting engine, it's also possible to extract this information.
Peter, you've got 5 minutes left until your
I have some further reading. I've uploaded the slides. All these things are the links. You can read the protocol specification. It is written in an RFC style document, except it's more like a blog post than a spec, but it's very good to go through and very easy to read. Some documentation on how to actually use it if you're using DNSDist, and some links to the issues for the other open source name servers, where you can ask them to please implement this or help testing. And if there are any questions, I will be happy to take them.
Thank you, Peter. That was actually a new idea for me, but well, we have some questions. Hazel Smith asks, in a direct server return case, your backend would already need to be able to speak for the VIP. The rest came into what? Would there benefits to the proxy2 protocol in that case versus using, for example, the GRE NCAP?
I don't know. That is my my honest answer.
Hello.
Oh, probably Pieter knows.
So the direct server return case is of very limited use because most proxy situations these days, or at least many of them, actually involve protocol translation like DOT to plain TCP, etc. So the DSR case is quite niche, but I think you're right that in the cases where DSR could work, the GRE NCAP would work just as well, except I'm not aware of any name servers that can parse those GRE headers. So you'd have to do that outside in the operating system.
Good, and
I
then
hope that helps. Yeah.
And then
Yeah.
Hazel says, "Thanks for the work."
You're welcome.
And we have actually Stefan wanting to ask a question. Please, Stefan, go ahead.
Yeah, thank you for the presentation. Stefan Ubbink from SRDN. I would like to know how it would work for the direct server return, because the client will get a response from a different IP. And if the setup is a TCP question, it should not be able to really answer to the resolver that is asking the question. How does it work?
In normal direct server return cases, the server has the IP of the load balancer configured as well, so it can respond from that address. Of course, you need some networking, your network to support that as well. And within the TLV, you can usually put all the TCP information that the original client has sent, like the window sizes, the SYN information, etc. So then the backend will set up the connection for you. Then load balancer will only point or send the information to the backend, and the backend will then do all the handshaking, and then your network usually knows what's going on there.
Okay, thank you very much.
You're welcome.
Okay, I would like to remind everybody to answer the poll. It should be up on your screen. There's a few votes missing, so please go ahead. Don't be shy. And with that, we come to Brett. Brett, please go ahead.
Hi, Peter. Yes, thanks for the presentation. It's the second time I've seen it in a week because I started the right meeting last week. And I'm going to ask the same questions I asked there because I think it might be useful for people here to hear it. So I'm just wondering if there's any plans to standardize this at the IETF, and if not, why not?
I'll give you the same answer I gave at RIPE. The answer is no. First of all, the protocol is already implemented widely. So the only thing that you could do is make an informational RFC saying, hey, it works like this. And last time we were trying to standardize some of this, which was XPF. The privacy advocates were not having it.
I think it's that in itself is a commentary on the IETF being dysfunctional if we are swerving away from standardizing things because the IETF is going to be aggressive towards them, shall we say. It seems like the thin end of a wedge.
You can take that comment as you wish. Although on the other hand, the protocol already exists. So like I said, only an informational RFC would make sense because implementations won't change.
Yeah, but I think that in itself might be useful. But you know, if we think it's going to be a waste of time, I think you might be right about that. But I think that's a commentary on the ITF, which maybe needs addressing somewhere.
Right. So we don't have any plans to start to standardize this, but we're open to voicing our support if somebody would. Let's put it like that.
All right. Thank you.
Okay. Thank you, Brett. And we have a question from Ralph Weber, and I am understanding correct that this is not multiplexing requests, meaning you have to have one connection per client from the proxy to the backend for TCP.
That is correct. That is how this protocol works, and that is also how it is implemented in the HTTP world. So on the HTTP proxy level. However, we are discussing with the original authors to maybe do a updated version where you could prefix multiple queries or requests within the same TCP stream. But that is just not in the protocol right now.
Okay, and then we have a comment from Ray Bellis, and he says, privacy objections, unwarranted IMHO were what killed the XPF draft.
Yes, that is absolutely right. The privacy objections were quite fierce and indeed quite unwarranted, because the protocol was explicitly specified to only work between two servers and not end to end. So yeah, I fully agree with Ray.
Good, and I think we have come to the end of the questions.
All right, excellent.
Okay. And
thank you very much for having us.
Thank you, Peter and Pieter. And I hope everybody followed this now correctly, because we'll be going back to the first Pieter. And Pieter Thomassen is talking about the querying the public suffix list via the DNS to us. Welcome back, Pieter.
Yes, Peter. Let me share my screen. Okay. Can you see my screen?
Yes, and we can hear you.
Okay, so I'm the same Peter as before from DSEC and Secure Systems Engineering. Yes, I will give a talk on the public suffix list and how it can be implemented or mapped onto the DNS and on the DNS query service that we run for it. So here's a quick public suffix list introduction. A public suffix is a suffix or domain suffix under which internet users can or could directly register names. Some examples of public suffixes are .com, .co.uk, and longer ones like, more common than this one probably is s3.amazonaws.com. And the public suffix list is a list of all those suffixes that are known. Yeah, so what does it mean? The public suffix list informs about policy and organizational boundaries in the domain space. It supports all kinds of things, including wildcards and exceptions from wildcards, and it's maintained by the community on GitHub, and the regular mode is provided as a text file. Yeah, so that's the public suffix list. What's it used for? So browsers use it for scripting, scoping, and cookie scoping. It's called the same origin policy, I think. For domain highlighting in the address bar so that you can see when you are at paypal.com.somethingelse.com. For phishing prevention, it's used by certificate authorities to ensure that people don't get wildcards for public suffixes. It's also used by DNS operators like us to prevent in a multi-tenant setup that people register public suffixes and therefore block other customers from creating zones underneath the public suffix like co.uk. And it's used by other technical standards like DMARC to identify the organizational domain, which is the one before the public suffix. Some call it the registrable domain. And it's used for email policy boundaries here. So the question is, why would it need a PSL query service from the DNS? I mean, all the applications I just mentioned already do work, but there are some downsides if you don't have a query service. So first of all, applications have to bring a copy of the list and they need to keep it up to date. They have to parse it, which is not trivial because extracting information from the PSL requires an algorithm that has 6 or 7 steps, I believe. You can check it out on the publicsuffix.org website. And if you do have a DNS-based query service, you don't need to parse and refresh anything. And it would be nice to have the capability to just use that query service to retrieve any domain's public suffix ad hoc with a simple lookup and even have that cacheable. And yeah, so that also means you can use standard DNS tooling or libraries, which is usually around, and you don't need specialized tooling. So here's how here's how we thought this could work. So we created a special zone and iterate over this public suffix list and take each public suffix and create a PTR record for it. And we use the public suffix both as the owner name under this zone and also as the value of the PTR record. So that means if you would query the PTR record for co.uk dot whatever the zone you're using is, it would mean that the response would be the public suffix of co.uk is co.uk. That in itself is not very informative, but on other names that you could think of, we configured such that they have a CNAME record or are covered by a wildcard CNAME record. And that means anytime you query something else, for example, example.co.uk dot the lookup zone, the CNAMEs would take care of the routing and you would still end up at this PTR record I just mentioned. So you can very easily retrieve any domain's public suffix by just querying, by prefixing that domain to the lookup zone and then querying the PTR record. In some cases, several rules apply to one domain name, and then of these several rules, one will be the winning one. For example, if you have a wildcard and then there's a wildcard exception, which the PSL specification does allow. In that case, only the final outcome will be given in the PTR record, and for documentation or studies or whatever people want to do, we give the other rules as TXT records on the same names. We implemented the whole thing under query.publicsuffix.zone, and authenticity is provided by DNSSEC. During implementation, there were some challenges. So as I said before, the parsing algorithm is not trivial. There's a bunch of precedence rules and all that. Also, the PSL rules almost match DNS data structures, but not quite. So there's things like inline wildcards that I will get to later. And also, if you have, say, the public suffix com, which gets a PTR record in our case, and then you have something like s3.dualstack.westeurope.amazon.aws.something, there would be a lot of empty non-terminals in between. So you need to have a CNAME chain to fix those up to be able to answer all the different questions for public suffixes on the intermediate level. Yeah, and so if you look at the 20K records that are necessary for PSL mapping itself, which includes the PTRs and the CNAMEs, then there will be an additional 55K records for signing and NSEC and all that stuff. So there's a pretty large zone that results from this. And if you do an incremental update, you have to calculate a very large diff and all that. So that was a little bit of a challenge too, but it was also quite a nice exercise to work our DSEC API on which we host this. Yeah, so this is a very quick screenshot of the code that does the central processing. It's just to illustrate how many steps there are, and essentially all of them correspond to one of the steps in the algorithm from publicsuffix.org. Here's a bunch of examples how to do these lookups. So standard case would be to do a PTR lookup on indico.dns-OARC.net .query.publicsuffix.zone. And as you can see, you immediately get covered by the wildcard.net PTR as for a CNAME record, which isn't shown as a wildcard here, but of course the indico.dns-OARC will fall under that, and it directs you to the net PTR record, and then that is getting looked up, and the result is that net is the public suffix of indico.dns-OARC.net. Another example would be a longer one that I mentioned before, s3.dualstack eos1 amazon aws.com. If you look that up, you will, because that is a public suffix, you will immediately hit the PTR record and will just get that response. However, S4, for example, is not a public suffix. So if you query for that, as I mentioned before, we have to fill up all these different empty non-terminals with CNAME chains. And so you get directed from S4 to dual stack and from dual stack to EU West 1 and so on and so forth. And in the end, it tells you that the public suffix of that name is .com. So one could say that's not very elegant, but if you want to do this in the DNS, as far as I'm aware, that's the only way of doing it. To give you an example of having additional rules documented in text records, we can look at wildcards with exceptions. So here we're looking at www.ck, and you can see that the result of that is that the public suffix is star dot. So that means the last label is the public suffix, just ck. So your application needs to know that, but that's kind of simple. And we also wrote a library that interprets things accordingly. You don't have to know it yourself. So all top-level domains, by definition, are public suffixes. It's not my definition; it's a definition of publicsuffix.org. And so CK would be the public suffix here. However, there's a text record telling you that star.ck is also public suffixes. So for example, foobar.ck would be a public suffix, but there is an exception, www.ck is not a public suffix. So the parent public suffix applies, which is the top level domain. So this is how this wildcard exception stuff works. As far as applications are concerned, they would only have to look at the PTR record. We implemented this under query.publicsuffix.zone, so you can try out these things with dig yourself if you like. We also have a website on publicsuffix.zone, which has a live demo. It's just a form that sends JavaScript requests to Google's DOH resolver and displays the PTR answer on the page. And there's a Python implementation. It has a library and a CLI for both doing lookups and interpreting things accordingly and showing the text records if you're interested. It also knows how to parse the PSL and output API payload to do the updates in the DNS using our own DNSSEC API, but the library itself is agnostic of the DNS provider. So if somebody else wanted to set up a zone like that on a different DNS provider, it would be quite trivial. One would have to write one function that transforms the output in the corresponding JSON or whatever the API needs and put it in as a very simple class. And then the same library can be used as is. There are some limitations. So as I said before, the PSL does support inline wildcards like foo.wildcard.example.com, and the DNS doesn't support that. So if you ask for the public suffix of such a domain, you will not get a PTR record. You will only get the text records telling you that those are the rules that apply, and it can't really be mapped into the DNS. However, the good thing is that the PSL doesn't actually contain such entries at the moment, and the maintainers are considering to drop this feature, so to speak. So this limitation isn't really a limitation currently, practically, and it probably also will not be a limitation anymore theoretically in the future. So in practice, the DNS implementation fully covers all public suffixes that are currently defined. Other limitations are on updates. We currently trigger updates manually. That's because the public suffix list usually in applications isn't up to date anyways, because you have to install a new version of, let's say, Chrome or Firefox to get the updates. So it doesn't really depend on the day, but it could easily be automated using a GitHub action or the GitHub Atom feed because the whole thing's managed on GitHub.
Peter, you've got 2 minutes for the Q&A.
Yeah, thank you. The question is, what should be done with this? So for us, it works perfectly well for the internal use case at the DNSSEC to keep customers from registering public suffixes and messing with other people's attempts to register zones underneath them. So that's fine. So we're completely satisfied. It works pretty well. It has been working for 2-3 years. However, we are very happy to make this a service that is of greater use to the community. The question is if there are such use cases and whether they would need automated zone updates, in which case we could implement that. Also, the public suffix list first has the section of icon, TLDs and all that, and then the private section, like the Amazon stuff. It's currently not mapped onto the DNS. I mean, this flag is not mapped, so you can see from the DNS lookup to what section the public suffix belongs. So one could also think about whether that should be changed. And so if this should be made a more useful service for the community, we're also happy to discuss how it could be run. Maybe there should be some, I don't know, somebody having the hat on, or maybe it's enough if we do that or all that. We just wanted to put the idea out and are happy to discuss all that. There are also some privacy concerns, obviously, because the PSL lookup authoritative server would learn the domain names that people query. So maybe it wouldn't be a great idea to use this stuff in a browser, for example. Just like OCSP would be leaking things. However, one measure to prevent that would be that a resolver could have a local copy, for example, of this zone. I'm not saying this should be done, but there's various ways of handling those kinds of concerns. I have a backup slide on that if that is what everybody's interested in. And otherwise, I'm happy to take your questions.
Oh, thank you, Peter. And as always, please type your questions in the Q&A pod or raise your hand and we will open the mics for you. And as always, answer the polls. We really would like to get information back and to the program committee to see if our assessment of the speakers matches what the attendees say. So, and it's you we do this for, so please give us some hints what you like. Yes, so we have a first question here, Peter. Greg Charles asked, what with the S4 example, do you have to have CNAMEs for every level?
I think so. So the alternative would be to have a CNAME at, let's say, star.com, right? Just like star.net earlier. And my understanding is if you have star.com CNAME, you know, pointing to the com entry, and then you add the S3 PTR record with all the intermediate layers here, then that would make the wildcard not apply on the intermediate levels, I think. At least I believe I tried that and it didn't work, or at least didn't work reliably. But maybe somebody else who knows more about DNS resolution can weigh in.
Hello, this is Peter van Dijk at Power DNS. What you say is correct. Those empty non-terminals would otherwise avoid wildcard matching. So as far as I can tell,
those nodes, those nodes exist in the DNS. Well, without the S3, they wouldn't be existing, so they would be covered by the wildcard. Yeah, I remember.
Exactly. So as far as I can tell, you do need all those CNAMEs, yes.
Good. And then we have a question from Jarle Frederik Rijpsland. And wouldn't it make more sense to have the zone operators publish something like this for their own zones, in the zones maybe? Then one could do away with the central management of the PSL and just rely on existing DNS delegation infrastructure.
I think there is discussion about that on the PSL mailing list. The discussion is, I think, 3 years old or something. I don't remember the different arguments. Somehow, apparently, participants of the discussion reached the conclusion that the PSL is still beneficial, needed, or necessary. And by the fact that it's used in browsers, I would think that probably that is correct, but I can't give you any precise reasons. So I would refer you to the PSL mailing list, which is, I think, announced or advertised on publicsuffix.org. And there's also the GitHub repository where the PSL is maintained. And they have a bunch of issues for improving the PSL, for example, dropping this inline wildcard stuff. And if I remember correctly, there is also an issue about the question you raised. So I would also refer you there.
Good. Well, I don't see any more questions, Peter.
Thank you.
And, thank you very much. And so with that concludes our morning session. Thank you for having me as your host. We now have a long break, lunch break, and we will convene back at 1:30 UTC. So yeah, enjoy your lunch and see you at 1:30.
Hello, everyone. Jacob Zach on behalf of the DNS-OARC Program Committee. I'd like to welcome you back to OARC 36, Day 2, Session 3. Our timekeeper for this session is Willem Turp, and we'd like to thank our sponsor, VeriSign. I'd like to welcome Tijay Chung from Virginia Tech, who will be presenting Understanding DNSSEC Debugging Patterns using DNSViz. TJ, whenever you're ready, you can share your slides.
Yep.
There you go. Perfect.
All right. Yeah, thanks for the introduction, Jacob. So I'd like to talk about understanding, the title is Understanding DNS Debugging Pattern using DNSViz, and the subtitle is DNS Challenges from the Administrator's Point of View. So this is joint work with Casey DCO from Brigham Young University. So let me start it. So we all know that DNSSEC is really important. So that's why we are here. So DNSSEC provides integrity and authenticity of DNS messages. But the thing is, there are recently more and more new internet security protocols introduced that rely on DNS and DNSSEC. In email security domain, MTASTS, DANE, TLSA records, and BME are introduced. For HTTPS performance and security, HTTPS record also recently introduced. And also, this is really great news that DNSSEC deployment rate is increasing. So this stat is from borrowed from DNSSECtools.org. So when you consider the most recent snapshots, the number of DS domain names with DS records set is over 70 million, which is really great. And I briefly mentioned DANE. DANE is to secure email protocols by introducing a new DNS record type, which is called TLSA records. As you can tell, the percentage of domains with TLSA records is really increasing. So when you consider, for example, .se, nearly 40% of domains with MX records, they enable DANE as well. But the thing is, server-side management, DNSSEC management is sometimes challenging. So left figure shows the percentage of domains with specific failure reason. So this graph is a little bit outdated. So most recent snapshot is December 2016. So for example, expired and invalid signatures ratio is under 1%, which is not that bad. But when you can consider the percent of domains missing DS record is sometimes over 30%. So which means there must be something wrong. And also, if you attended yesterday's talk, we all know that Slack.com experienced some DNSSEC outage because of its bogus status. And NSF.gov is also was experienced outage for 2 days. So in this research, we would like to understand what is the most challenging things for DNS administrators to manage DNSSECs. So far, there have been lots of approaches to understand this specific questions using passive or active scans. But the thing is, their time granularity between each scan is a little bit long, such as a day or sometimes a week. So we decided to use DNSViz. If you're not familiar with DNSViz, please check this website, DNSViz.net. It is a really awesome tool for visualizing the status of DNS zone, and it is built and managed by KCDCO, and it helps DNS administrators deploy and manage DNSSEC. So I am a big fan of DNSViz. So if I'm managing my domain name, if my server setting, DNSSEC setting is something wrong, I go to this website and check the status, my domain name. If it's still something wrong, I change some configuration of my server and I check this website again. So if you type DNS-OARC.net at DNSViz, then what it does is it basically fetches a numerous DNS records from your authoritative DNS servers, and based on the results, it analyzes the domain name. Because DNS-OARC.net is managed perfectly, you don't see anything wrong with it. But if you type DNSSEC-fail.org, you can immediately notice that, oh, DNS key is not matched with the DS record. So the chain of trust is basically broken. So all the DNS records signed by DNS keys cannot be verified. So the status is bogus. So how's the DNSViz data set looks like? So it spans from 2014, 2021. So it is quite longitudinal. And the number of domains inputted by user is 800,000. And the percentage of signed domains is nearly 30%. So when you consider the percentage of signed domains under, for example, .com, second level domain names under .com is nearly 1%, it shows that lots of DNSSEC administrators actually use this website for their debugging or managing their DNSSEC settings. But I mentioned briefly that we are only interested in DNSViz analysis requested by actual administrators. But the thing is, DNSViz is publicly available, so anyone can just go to the website and type a random domain names as I introduced. So distinguishing this domain name from the analysis requested by actual administrator is really challenging. So our first approach is we would like to filter some popular domain names. So this graph shows the average number of snapshots of domains depending on their popularity. So as you can tell, the more popular domain names seems to have the more domain names analysis. So for example, because random users just go to the website and type google.com and facebook.com. So we would like to filter out such popular domain names from our analysis. And second one is DNSViz.
3 minutes remaining.
Yep.
3 minutes remaining until your 5 minutes Q&A time.
All right, thank you. DNSViz used to self-scan. So they used to scan some domain names every 48 hours or 8 hours. So we decided to remove such domain names only if these domain names have analysis of which time differences between consecutive to analysis are 48 or 8 hours. Yeah. So the domain names we are interested in now is 94,000, and the percentage of signed domain names is nearly 85%, which is really great. But the thing is, the percentage of signed but ever bogus domain names, sometimes they their domain names turn to bogus domain names. So administrators go to the website to fix their problem. So the percentage of this domain name is over 26%, and percent of signed but ever unsigned, which means they retracted DNSSEC, is near 10%. So the first preliminary analysis is DNSViz really helpful? So we simply try to compare the only first snapshots of the domain name analysis and compare them with the only last snapshots of their domain names analysis. So as you can tell, this graph shows the status, the percentage of status of domain names. We can see the valid percentages jumped nearly 20%. So DNSViz is actually helpful for administrators to fix their errors. And we can also estimate the most common errors. So as we might expect it, the missing DS record is over 57%, which is not a good news. And also because the domain name owners use DNSViz multiple times to fix until they fix their errors. So we can briefly estimate how long does it take to fix a specific errors. So on an algorithm, which shows the longest time, this is the errors when the algorithm number is not defined in RFC. So it is rarely fixed. And after that, we can also tell the missing DS record is the second ranked, the errors that takes the longest time. So we have, so I have shown you some preliminary analysis using DNSViz. So our future step is we try to understand the relationship between each others, because DNSSEC may, one adder may cause another adders. So if we could figure out what the root causes of these adders, then we can expect that this analysis may help for administrators to fix the subsequent adders. And we expect that depending on the managing entity, so for example, who manages the DNS software, such as registrar or domain name owners or third-party DNS operators, we might expect that the DNSSEC management quality might be different. So, yep, this is it. And it would be really great if I could hear some suggestion or the comments of this analysis. Thank you so much.
Thank you, TJ. Everybody, you should see a survey pop up shortly for TJ's presentation. This helps the program committee, compare our numbers versus yours. Okay, so we do have some questions already queued. I recall there were times when data wasn't collected by DNSViz. Is it continuous collection from 2014 on? Asks Allison Mankin.
That is a really great question. So as far as I know, near the 2018, there was a the missing snapshots around a year, I guess. So near the end of 2018 or so. Yeah.
Okay. Peter Thomassen asks, how can there be greater than 200 analyses per domain on average when only the top Alexa bin is above 200?
Let me try to understand the question. How can there be more than 200 analyses per domain on average when only the top Alexa bins is above 200? So the Alexa bin above 200 means if the bin is 200, it means the domain name is really popular. So it means throughout the period, entire 6 or 8 years, we found that this domain name at least has been scanned by DNSViz at least 200 times. So yeah, I hope this answered your questions.
Okay, Peter Thomassen also asks, on slide 16, what's the difference between insecure and not deployed? Oh,
this is a really great question. So not deployed is a not specifically defined term in RFC. So insecure is the DS record is simply not uploaded, but not deployed is, I'm sorry, insecure means even if a domain name has a DNS key, but if it does not have a DS record, it is insecure. But not deployed in our definition is it never tries to deploy DNSSEC at all. So not introducing any DNSSEC related records.
Okay, Moritz Muller asks, what is the most common error of domain names that got fixed?
Yeah, this is really a funny answer. So if the signature is premature, not yet valid, then it is automatically fixed as time goes by.
Kathy Almond asks, does your analysis consider that DNSViz may also be used for checking delegation and other potential issues, and not only for DNSSEC signed status validity?
Does you consider DNSViz? So we are only relying on DNSSEC validation status. So I have to check with the developer case Ducio if it also has some reasons, such as if the server experienced a simply outage or the server is offline. But the current analysis are just based on DNSSEC validity. So by validating all the DNSSEC records.
Okay, and we have a live question from Matthew Poundsett. I'm going to allow you to speak, Matt, if you want to unmute yourself.
Hi, thanks, TJ. You sort of expressed, it sounded like disappointment at the high missing DS statistic. Yep. I think if you sort of look at the way operators will tend to use this, then that shouldn't really be surprising. So if somebody's deploying DNSSEC, they're going to go and check their unsigned zone, make sure everything is good, then sign it, and they'll check it again to make sure all the signatures look right and everything, and then add DS records, and then check it again. So you'll always see a high rate of things like missing DS and missing RRSIGs and things like that. And sort of actually to add a bit to that previous question, yes, DNSViz gets used a lot by people who are not interested in testing their DNSSEC. They're testing their domain, and so yeah, there will be a lot of that in there as well.
Yep. Regarding your first comment, so if we do you think it is kind of, how to say, it'll be worth it by measuring how long does it take for administrators to let their DNS, RRCs, served, but without actually serving DS record? So basically try to measure how long it takes to prepare actual DNSSEC deployment.
Yeah, you might be able to identify, you might be able to pick out people who are using it to test a deployment versus just generally testing their domains that way. By looking for sort of short periods of time as they progress through these steps of deploying RRSIGs and then deploying DS.
Gotcha. Thank you so much for the comment. Yeah.
All right, it looks like there are no further questions. Thank you very much, TJ, for your presentation.
Yep. Thank you so much for this opportunity. Yep.
Right, our next speaker is, oh, I'm sorry, a poll will pop up. I think I mentioned that earlier. Our next speaker is Kundana Pillari from UC Irvine and Salesforce, who will be giving a presentation on, or titled A DNS Anomaly Detection Model to Identify Unusual Lagging and Zone Updates. Kundana, if you want to share your slide. Perfect. Please proceed.
Hi, everyone. I'm Kundana Pillari. I'm currently a second-year student at UC Irvine, majoring in CS. And this past summer, I worked as a SWE intern at Salesforce in the public DNS team, where my project involved building a DNS anomaly detection model to identify unusual lagging in zone updates, which is also going to be the topic of my talk today. So just some background, in large-scale DNS deployments, zone updates are made by DNS hosting services on short timescales to large number of servers. And it's normal for these updates to be somewhat asynchronous from each other. But for our organization, customer sensitivity to stale information is high, and we want to take action by asking the hosting services to check for server problems when there are anomalous lags. So the question here is which lags are anomalous and what threshold of difference in the SOA serial numbers indicates a problem. So to solve this problem, I used an unsupervised machine learning algorithm to identify the anomalous data points in the monitor logs to help with the question of what is actionable. So scope of anomaly detection in DNS. This is the zone infrastructure at Salesforce. Athena is a system built by the public DNS team at Salesforce that sends dynamic updates to a hidden internal server called Sabre, which then updates the external servers. And the particular servers I looked into are UltraDNS and PCH. So the scope of my work is to find update latency anomalies in these external servers sent in this process. So initially, I explored through multiple platforms and algorithms to build my model. And this includes looking at TensorFlow, PyTorch, and also PyCaret. Ultimately, I decided to use the PyCaret open source machine learning library, mainly because they have more algorithms geared towards unsupervised learnings and more specifically anomaly detection. So in machine learning, there are two types of learnings, supervised and unsupervised. And in unsupervised learning, you're not giving a specific target for the model to focus on. Instead, the model uses clustering methods to learn on itself, different trends and patterns in the dataset. So there are many algorithms regarding unsupervised learning, and this includes KNN, we support vector machines, principal component analysis, and also isolation forest. So I decided to use the isolation forest, or also known as iForest, machine learning algorithm, mainly because it requires less memory and it's faster in performance, and also traditionally used for anomaly detection for these reasons. So just some background about isolation forest. It identifies anomalies by basically isolating the outliers in the data. It works on the principle of the decision tree algorithm, which randomly selects a feature from a given set of features and forms decision trees using those combinations. And outliers are basically the ones that are closer to the root node and they're easy to isolate, and regular data points are the ones that are farther from the root node and difficult to isolate. So my model was trained on the monitor logs, more specifically the May and June monitor logs. And I only looked to 3 production zones. Those were my.salesforce.com, salesforce.com, and force.com. And I only looked to the SOA records. So the key details in the data set that I focused on are the probe time, that is the timestamp, and also the details section where each server is represented by a serial number that indicates their zone version. So to improve my model's performance, I also fine-tuned it with the supervised target, giving it as a probe time to control the learning process a little bit and improve the performance. So the output from the model is the same data, you feed it into it, but additionally, it marks each data point as normal or anomaly. And additionally, it also gives you a specific anomaly score, where the higher the score, the more anomalous the data point. So going into analysis, the idea was to look at the serial numbers or the zone versions. And so I found the average differences between the normal and the anomalous data points. And for comparison, I also found the average differences just between the normal data points. So here, for example, for salesforce.com, you can see that the difference between the normal and the anomalous is around 63, but just between the normal data points is around 0.27. So this gives you an idea of how much lagging there is and how different it is for all 3 zones. So yeah, using the output from the model, we can learn different trends and patterns in our zone updates, and more specifically, get the thresholds for our zones, which we can integrate in our monitoring system. So as I mentioned before, the main goal of this project was to provide good numeric thresholds for how much lag was normal and how much lag was anomalous. And this was more important because previously the thresholds were guesstimates made by the team, and they were same for all 3 zones. But the output from the model clearly shows that the anomalous behavior for all 3 zones are extremely different. And it depends on the zone sizes and how frequently the zones were updated. So the next steps in my project was to include dynamic texting. And this is to writing a Python script that periodically calls the models on new data points to generate new thresholds and then integrate them back in the refocus dashboard that is our monitoring system at Salesforce, and also to have logs to preserve previous thresholds. Additionally, another idea was to send alerts for the highest anomalous data points. This is through email or PagerDuty. So overall, ML has been used on DNS data frequently, but it mainly focused on DNS attacks and security. However, this work focuses on DNS availability, and ML models, both unsupervised and supervised, can be valuable to many other areas in DNS operators, have data in real time in future. And this project is just one of the applications of ML and DNS, which helps us to understand the abundance of data that we get from the infrastructure. So thank you. That was the end of my presentation. If you have any questions, I'll be happy to answer them.
Thank you, Kundana. There should be a survey popping up for everyone. If you can fill that out, that would be wonderful. And our first question from Pieter Thomassen. Great research. How come the thresholds depend so much on what zone it is? You mentioned zone size as a reason. Should that really play a role when using IXFR as stated on slide 4?
Yeah, so I think from the model, like let's say for my.salesforce.com, it's one of the biggest zones, but for force.com, which is a really small zone, we saw that for big zones there was much lagging, but for really small zones there wasn't much lagging at all. So it really tells us that how often they were updated, and the zone size play a huge role. And this was just one of the understandings from our project. So yeah.
Okay, I see a question from Stefan Ubbink. If you can unmute yourself.
Hello, Stefan Ubbink, SRDN. I was wondering if your research only was applied to logs that you have, or was it also applied to real-time analysis of the current state of the DNS setup of Salesforce?
Yeah, this project was just based on the logs that I had. And actually another step was also to integrate that in real time through the dynamic testing. But I didn't have much time in my internship to work on that. So I just focused on the logs.
Thank you very much.
All right, and I see a question from Brett Carr, if you would like to unmute yourself.
Hi, Kundana. I think this is a really, really great application of machine learning, certainly from somebody who's been operating DNS infrastructure for TLD for many years. We've often suffered from propagation of zones lagging behind and alerts going off and then catching up again and wondering why. And so I think we'd really like to take a look at this. I was wondering if you're planning to open source any of your code or anything like that, so we could maybe take it and help you improve it, etc.
Oh yeah, for sure.
Okay, good, thank you.
All right, I see I guess one additional comment from Alison Menken saying, additionally, the bigger zones change more frequently, Pieter Thomassen, and there are many IXFRs to get disseminated. I guess that's not a question. All right, any further questions for Kundana? Well, thank you very much for your presentation, Kundana.
Thank you.
And next, we'd like to welcome Stefan Ubbink from SIDN, who will be presenting disaster recovery with DNSSEC.
Hello, my name is Stefan Ubbink, and I'm a DNS and system engineer at SIDN. SIDN is the registry for the .nl zone, which is the CCTLD for the Netherlands. We also host a few other TLDs, and this is an overview of the things I'm going to talk about today, and we get right onto it. So why this talk? Earlier this year, we replaced our HSMs, and to get a better understanding of what we have to do in case of an emergency, we created some what-if scenarios. And one of the scenarios was where we would lose all our keys. Since we make a backup of our keys, we could recover from that incident by restoring the keys from the backup. Or not, because we don't create the backup of every ZSK. It was a possible issue here. The KSK has a longer lifetime and is available in every backup we make. So the KSK could be restored always, but the ZSK not always. Here I have a picture of our signer setup. It uses 2 data centers, and in both data centers there's a chain of systems that leads to a signed zone which is published. The most relevant parts are the signers and the HSMs. Here noted as ARN2 HSM P1 and ARN2 sign P1 for one setup or one data center, and the other data center is either one sign P1 and either one HSM P1. The HSMs in this setup are in high availability cluster. So when one HSM falls out because the data center goes away, the keys are still available. If you lose the keys, there will be a start of loss of service. because no updates for the zone can be done until the keys are back. And if you don't take any action, domains will start to fail because the RR6 will expire, and the last RR6 that will expire will be the one of the server records. In the previous setup, the KSK was always in the backup, so we would be able to restore that, but the ZSK might not be in the backup, and if that cannot be restored, the ZSK, the new ZSK has to be introduced. This will mean that all DNSSEC signed zones will be unavailable for the TTL of the DNSSEC key and or RR6. For .nl, this means an outage of at least 1 hour, and because of 60% of the resolvers used in the Netherlands validate DNSSEC answers, a lot of people will notice it. Yesterday there was a remark in Mattermost that press is always good, but I don't think this will be good press for SIDN. So what have we done to prevent this from happening? We could remove the DS from the parent, but that doesn't make it possible, and this will make it possible to publish a new unsigned zone after the DS TTL has expired at the parent. But this is only a last resort and will mean that every other zone under the NL will go insecure. So the items mentioned earlier today, like TLSA records, will no longer work, and this will be a big impact. To be able to restore from the backup, we would have to make a backup every time a ZSK is created. For .nl, this is every 90 days. But we also have other TLDs, like I mentioned before, so that would mean a lot more backups. And we do not really want to do that that often, because it's a manual process and needs some people at site, at the office. To be able to do everything correctly, we have to have a correct fitting procedure which we can follow to create, but also restore the backups. And you have to test these regularly. We found that OpenDNSSEC, which we use, has a good way to prevent not backing up, not forgetting to back up a ZSK. We made some adjustments to the configuration by setting the require backup option and setting an automatic key generation period with a good value. What a good value is depends on your situation. For us, this is 1 year. So we can generate ZSK in advance, or OpenDNSSEC will generate keys for 1 year in advance, and we will make sure that we make a backup every half a year. If you use the wrong value there, OpenDNSSEC will create a lot of keys, and during deployment in acceptance, we noticed that it generated 4,000 keys, which made some tools a bit slow. To make sure that we do create the backups at the right time, we created scheduled tickets for creating the backups. And we also changed the timers for the refresh and the resign time. Because as you can see in this picture, there is a reaction time in which you have to react, and otherwise the zone will be in problem, will have a problem. We decided to have 7 days of reaction time because we think we don't want to have to break off our Christmas dinner because there's some issue with the zone. And we calculated 7 days would be a good value to prevent this. I would like to thank Barry van Haderen from NL Labs for providing very excellent explanation about the possible impact and ways to act in this what-if scenario. And I would like to thank my SRDN colleagues for helping improving our DNS setup. And I'm glad to answer any questions that are available for me.
Right, thank you, Stefan. A survey should pop up shortly for everyone to rate this talk. And are there any questions for Stefan? I suppose I will start with one. So I similarly had an issue with DNSSEC where there were many thousands of extra keys created. And I guess I'm curious, do your HSMs talk to each other, or were they created on one HSM and not the other? And how did you deal with that scenario?
We have a separate HSM for our acceptance environment, and it created the keys on both HSMs because they are in high availability mode. So if you create one on one HSM, it will also automatically create it in the other one as well. But if you delete it on one, it will also delete it in another one. So that was very easy. And when we noticed that much keys in acceptance, we just removed the partition, created a new partition, and started from scratch. That was the easy way.
Sounds like what I would do. All right. Any other questions for Stefan? All right. Well, thank you very much, Stefan. Great presentation. And with that, we will go into our break. The break begins now. We'll call it 18 minutes instead of 15 minutes. We will be returning at 14:30 UTC sharp. Once again, we would like to thank our workshop sponsor, VeriSign. See you at 14:30. Hello, everyone. Welcome back to OARC 36, Day 2, Session 4. I'd like to welcome Brad Ellis from the Center of Excellence in Next Generation Networks, who will be presenting independent performance verification of XDP-accelerated not DNS. Brad, if you'd like to start sharing your slides, everything looks good.
Thanks, Jake. Is my audio okay?
Audio is good, sir. Please proceed.
Thank you. Hi, everyone. My name is Brad Ellis. I'm a solutions engineer at CenGen. I'm going to take you through the independent verification of XDP-accelerated not DNS. About me, I'm a solutions engineer at CenGen. We are a not-for-profit based in Canada. Our mission is to aid the commercialization and growth of Canadian startups and overcome technical challenges that are currently inhibiting them. We're funded partially by the government, but also largely from industry through memberships, a summit that we do similar to OARC, and a couple private revenue projects as well. Oops. Just an agenda, we're going to go over the test methodology of what we did, some of the background, a couple attempts, some technologies that we investigated, and then finally some performance results. And we're going to measure up to CZ-NIC, the guys who actually wrote NOT, and compare it to their results as well. So for a little background on this project, CIRA, the Canadian Internet Registration Authority, reached out to us to see if we could help them achieve their goal of 10 gigabits per second or line rate of UDP DNS responses, or get as close as possible. Doing that, we'd want to document setup procedures and then ultimately recommend system sizing in order to do that. So if you're going to go and buy new servers, you want to get the cheapest ones or the smallest ones possible to achieve the ultimate goal of line rate UDP responses. In addition, we're going to do what we could to investigate the possible speed up of TCP responses as well. So in our test topology, and I'm sorry for the ASCII, but it was kind of the best way to get all the data in a nice concise format. We have 3 DNS load generators through which we'll run multiple instances of a load generator and pump all that towards one single DNS server. On that server, we're going to vary the amount of CPU cores enabled so that we can try and find that sweet spot of how much CPU is needed, and then measure memory usage and so on to try and find that perfect system sizing. As well, doing this, we wanted to make sure that since the DNS server would be like multi-threaded, we wanted to multi-thread and multi-queue the load generators to make sure those weren't ever the bottleneck. We wanted to make sure it was always at one server. So on the load generators, as I mentioned earlier, we had multiple instances run across them. We use scripts to start those instances, stop them, collect the results, aggregate them, and get kind of a final number of the number of responses we got, per second or in total. Each load generator had a dictionary that was derived from the full zone that we were testing. The records were requested at random, and we made sure to only have 100 outstanding queries to try and keep results somewhat fair, rather than just like hammering the server, bogging it down and just waiting for a bunch of things to time out that might give us a less accurate response. What's worth noting is that even though we used a dictionary derived from the full zone, we didn't find an appreciable difference between using a full dictionary or using a smaller dictionary of only, say, 1,000 different queries to send. We just made sure that we were doing a number of different types of record requests. So like A's, quad A's, NS, DS, etc. So with the baseline, we replicated what Sierra had set up, and we tried to achieve a number similar to what they were achieving to make sure that we were starting on even ground. So this was a Bind9 authoritative top-level domain running a full real zone. And once we got that all set up and we ran some tests against it, we were seeing roughly 120,000 queries per second response. So that was about what Sierra was seeing. We found that we had low network utilization, like 168 megabits per second, and relatively low memory and CPU utilization. We saw no obvious hardware bottlenecks preventing us from going to higher scale, like we were running out of CPU or memory or anything like that. So this was where the real challenge started, is figuring out what was limiting us, how to get around that, how to increase that number. So first we did a couple hardware tweaks, changing BIOS profiles, etc. We kind of ran through a bunch of those and eventually landed on an IO optimized profile. We turned hyperthreading off, and we saw like just over 100% improvement in that we were able to get around 250,000 queries per second, although that did up the CPU utilization to about 60%. So with that, we started to see a bit of an issue where we could get better numbers, but CPU was growing kind of roughly linearly with those. So what we did is we decided to expand on that. We made the application cloud native. So we deployed this in Kubernetes by building Bind9 pod and a custom deployment with load balancing, auto replicas, and so on to scale that out. This was successful in that we were able to fully utilize the hosts, and it accelerated kind of the management or adding on of more hosts and getting them going. However, we still only saw about 500,000 queries per second, still less than a gigabit per second per host. So it was an improvement, but obviously not quite what we were looking for. So we started looking at some new technologies that might help us along, because clearly we're not CPU limited or something like that. And we found that one technology, XDP, would be very useful in kind of what we think is going on here. So XDP stands for Express Data Path, and ultimately it's there to improve network performance. The way it works is it moves many functions lower in the networking stack. So for example, to kernel level, or even in some cases, some network cards actually have hardware that can run XDP programs, which can greatly speed up like network throughput, packet decisions, and so on. So the result of this is it frees up quite a bit of CPU. It moves things lower in the stack. It means that some actions can happen sooner, since fewer things need to be punted up to the CPU. And in many, many applications, this is used for doing routing decisions, packet filtering, and so on. So it can be very effective in many, many packets coming in, making decisions, and sending them out. XDP, however, comes with a fair few number of limitations. First is that XDP needs direct access to the network card. This can be quite difficult in a virtualized environment, still possible, but it means that in our case, we stuck with, instead of running virtual machines, running on like bare metal servers. Another huge one is that we need symmetrical packet paths, which means that you need to make sure that a packet coming in on one interface, the response goes out on the same. So we can't do things like NIC teaming, or in the case of Kubernetes, it's very hard to make sure that a request coming in on one server is responded by that same server. So the load balancer can create a problem then, and the load balancer itself becomes a bottleneck. And then finally, like the kernel has to support XDP and have it enabled. This is no longer an issue. It's enabled by default on all the latest kernels for shipping with distros. At the time, though, it wasn't. So I had to find one that had it enabled. I had to sometimes recompile the kernel to make sure that was enabled as well. As I alluded to with Kubernetes, it's hard to enforce that symmetric packet path. And you also need a network plugin that will do the XDP in place of the application. Because Kubernetes has more of the context of like what pods are running on what hosts and so on, it really needs to take care of that. So you do lose some performance in that pod to network plugin interface. So now that we have XDP as a target, we're looking for ways to get this enabled. We tried the Kubernetes route. It didn't really work for us. And then we reached out to CZ.NIC, the guys who wrote NOT, because they had it enabled in NOT. And we worked with them over the past year or so to get that going. And as it turns out, it's incredibly easy to enable XDP in NOT because they have a YAML-based configuration. All it takes is a top-level element of XDP. You turn on listen, and then you're already working with UDP. TCP, there's just a couple more options to configure. I just say TCP on, and then max clients, buffer size, and so on. These numbers are really about tuning. So I have some examples here. They won't necessarily work the best for you if you go to replicate this, but it is an example. And then finally, with a faster DNS server, we need a faster tester. So historically, we were using DNSPerf, which was a great tool. It gave great results output at the end. However, it just could not keep up with the new server. So I think we were able to get like 200,000 queries per second from each DNSPerf instance. But if we're kind of extending this to new orders of magnitude with XDP, we need an XDP-enabled load generator, which is what KXDP Gun does. And then we also discovered that KXDP-gun automatically creates a number of threads equal to the number of queues configured on the NIC. So we didn't have to do any extra work to make sure that matched and it was optimally there. So once we had the XDP gun enabled and not with XDP enabled on the servers, we were able to get some performance results. And we ultimately hit 16 million queries per second using roughly 92% CPU. And the reason that we couldn't go higher than, say, 92% is because 16 million queries per second was 25 gigabits per second, which was the size of the network card we had. So we hit network card saturation. And we hit this actually at only 32 cores when we had 36 available. So there's room for a little bit more improvement there, although that's the limit of what we hit. For some context, this is like 133 times our baseline number. So this was like a great performance result that we got, great improvement. Next, we're going to focus on TCP results. So this is a little bit harder. It takes more tuning and so on. Our baseline was around 40,000 queries per second without XDP on. So when we were doing this, NOT didn't actually have XDP for TCP. So we collaborated with them. And I don't want to overstate how much we worked with them, but they were a great group to work with, always answering questions. We did what we could to test new features, new config changes, file bugs if we found them. And towards the end, once kind of everything was working, we actually achieved a maximum of 1.3 million queries per second with TCP. Like 32 times our baseline. And what I've shown here in the graph, it may be a little confusing, but because TCP with its back off and stuff like that, we graphed like kind of the high result and the low result. This was over something like 100 iterations. So we actually found some pretty good consistency, graph the average here. And that's what we had there. So finally, because our numbers don't match up with what CZ-NIC published, because our server is completely different, we had to try and find a way to compare these. So we had different like CPU counts, different CPU speeds, and architecture. So like Intel versus AMD. As well, we had different NIC speeds. So CZ.NIC had a 40 gigabit NIC, while we only had 25 gigabit. So the best effort of what we could do is try and find a way to break this down to a more fundamental element. And so we attempted that with queries per second per core gigahertz. So that would be like if I had 36 cores at 2.3 gigahertz, I would divide my queries per second across 36 times 2.3. It's a very crude simplification. It doesn't account for Newman nodes, for example, like number of CPUs versus cores, and it won't be linear in that the higher you scale, you're going to get less per core gigahertz. But it at least gets us on somewhat even ground, so we can see, hey, are we doing this right? Are we on the right track? Did changing one thing actually make a meaningful difference? And so we were able to find that even though CZ-NIC had, I'd say, a much more powerful processor than we did and a faster network card, with UDP, we're actually able to slightly eke out a little bit more, queries per second per core gigahertz. But on the TCP front, we're a little bit behind there. So that indicates that we're mostly doing it right, but in our test setup, we actually need to tune that TCP server a little bit more to try and get that number up. So I think I'm doing pretty well on time. I'm open to questions now. I've also kind of included a couple links to, our company, to Sierra, CZ-NIC, and the utilities and tools that we used.
All right, thank you, Brad. Everybody, you should see a survey pop up for this talk. Please feel free to rate this talk as it's very important to the program committee. I do see a couple questions here. Hazel Smith asks, QPS over core gigahertz. Have you considered QPS over watt as a measure?
That is something I considered, although we weren't, at the time, we're not set up to measure watts. So I could do it based on, like the published like thermal dispersion unit of CPUs, but that wouldn't be realistic unless I actually had, calibrated test equipment to measure the actual power used by the server. As well, I could measure that, but I have nothing to compare it against because it's not something normally published by other people doing these sorts of tests. So great question, good like next step perhaps, but it's not something that we've done yet.
Okay, Kathy Almond asks, out of curiosity, what version of Bind 9 were you testing before moving on to XDP with NOT?
I don't recall. This was about a year and a half ago, but it was the latest version in like apt or any of the repositories that way. I didn't download from Git or anything like that.
Okay. Greg Chule comments, very interesting. He asks as well, which version of Bind 9? He then asks, did you consider thousands, 10,000s, 100,000s, etc. of different queries? 16 million QPS at 25 gigabits per second looks like 1,500 byte responses?
Good question. So we set our MTU to 9,000 so that it wouldn't be kind of limited to a specific 1,500. The average query response was 112 bytes. So that did vary. And for the number of different queries, I think you're referring to the dictionary that we used. So we used on the order of tens of thousands of different queries in that dictionary that were then chosen at random. Although, through iteration and testing, when we're converting between DNSPerf and KXDP gun, which use slightly different syntax in their dictionaries, we tried a short dictionary and we found that there's no appreciable difference as long as we had, say, roughly 1,000 or so, just to make sure that we had a large enough sample to get different types of queries.
Okay, we have a few questions left at this point. I think I'll cut off the question line. Peter Hessler asks, when you switched the DNS server software to NOT for XDP, did you rerun the baseline tests using NOT instead of Bind 9?
We did. They weren't comparable. Like NOT was actually it was actually quite a bit more performant even without XDP, although not recorded here because the ultimate goal of this was to compare against Sierra's baseline. So we recorded the data point, didn't find it super relevant, and just kind of stormed ahead to get that maximum performance.
All right. Peter Lexis asks, and this may be answered already, the QPS measured, was this for one Q name, random subdomains, existing names in the zone, etc.?
This was for existing records in a zone. It was only the top level zone, so no subdomains or anything like that.
Okay, and Thibaut Dublé asks, how are DNS query stats collected when XDP is enabled?
That's a good question. So I don't know the specifics of how exactly they do it, but I'm using the output given by KXDP gun. So similar to the way DNSPerf will give you a summary at the end of queries per second, queries sent, failed, etc. KXDP gun does the same. So because it's done at XDP, because it's done with XDP, there's not something I can do to say do a packet capture and see how things are coming in. I had to depend on the output from KXDP gun. And then from there, I aggregated them and added them up for the multiple instances.
Okay, Robert Story asks, did you do any testing with multiple NICs on the server side?
We attempted to at first. So that was one way to try and make sure that we weren't network card limited. So we tested with an Intel 10 gig, as well as an Intel 25 gig, and also a Mellanox 10 gig. We saw nothing, we saw no differences because at the time we were still limited by the server. Once we went to XDP, we very quickly realized, hey, we're going to hit like network card saturation. So we went with the fastest card that we had available, which was that Intel 25 gig.
Okay, a couple more questions from Kathy Almond. A potentially silly question, but when collecting stats on QPS, did you sanity check that the query responses were good, i.e. not serve fails potentially due to resource issues on the server?
Yes, like both of DNSPerf and KXDP-Gun gave a listing of how many responses of what type. So in KXDP-Gun especially, we made sure to use the responses of essentially OK, where it removed no responses, it removed serve fail, and so on. So we received more responses than put here, but I only collected and reported on the good responses.
Okay, and a follow-up from Kathy may already be answered. Actually, what kind of answers were you testing? For example, NX domain, no error, etc.
Yeah, so we used first a file provided by Sierra saying, here's the test that they used, and that included a bunch of like NX, A, quad A, DS, and so on. So I don't think I can respond too much farther than that, as I'm myself not a DNS expert. But I think I did my best to make sure that we got a wide range of types of queries. So for that, if you can put your question in the Mattermost, I can do my best to go research that and come back and let you know.
All right, and one final question, from a live question from Brett Carr. Brett, if you'd like to unmute yourself.
Hi, Brad. Yes, this is really interesting work, and the numbers that you're getting here are terrifyingly large, which is quite exciting compared to what we think our infrastructure can do currently. But my question really is, you kind of glossed over the fact that you thought this would be difficult to do using virtualization. And our infrastructure is completely virtualized currently. So I wondered if you could maybe expand on that very, very quickly, and if you've got any thoughts on, it would be possible on this type of virtualized infrastructure and not possible on this type of virtualization infrastructure.
Great question. Yeah, thank you. I did gloss over that in the interest of time, but once we figured out that we essentially had to do XDP to get further numbers, and I agree, when I first saw the result, I thought I did something wrong, but it turns out it is correct. So for virtualization, the application needs to program the network card with an XDP program. And in order to do that, it needs to be able to access the network card at least somewhat directly. At the time, and in the private cloud that my company has built, we didn't have the ability to expose that, let's say, XDP interface to a virtual machine to do that. So it is possible, but we found it incredibly difficult, and instead decided to storm on with actual like hardware bare metal. It can be done. I've done some research, but it required kind of reconfiguring the cloud that we built, which was OpenStack. I do know that VMware actually makes this a little bit easier, although it is a paid offering. So it's possible, but it's something that we decided was too difficult, given that ultimately Sierra, who hired us to do this, are looking for like bare metal, let's call it pizza boxes that they can install. So solving the virtualization problem wasn't one of our main goals.
Okay, well, I think maybe we get in contact after this, because that might be something we'd be interested in engaging with you on further.
Absolutely.
Okay, thanks, Brad.
All right, thank you very much, Brad. Great presentation.
Great, thank you very much.
All right, next we will move on to our first lightning talk. That'll be Petr Špaček from ISC presenting on the NSEC breakage survey. Peter?
Hello, can you hear me?
I can. Audio's good. Slides are there. Please proceed.
Excellent. Welcome to talk about NSEC breakage. It basically follows up the Slack talks. And the main motivation for the talk is that in the next version of Bind, which is coming out soon, we're going to enable the aggressive use of cache. So we just wanted to know what will break. So next slide, please. Just a quick recap. The type bitmap is a list of types which exist on a given name. So here on slide, we have the precise type bitmap. So we can see that on the name users.isc.org, only 3 types do exist. It's the A and a mandatory RRSEC and NSEC, and that's it. This is like the book RFC standard NSEC record. And the biggest advantage is that it allows resolvers to effectively use the cache, because the resolvers can synthesize no data answers when necessary. Next slide, please. An alternative how to do that is use so-called blacklist, for example, used by Cloudflare. And in principle, the authoritative servers return NSEC record with like the huge list of types, practically all the types the server supports. And it just flips down the bit for the type asked by the client. So here on the first line, the client is asking for TLS-A, and the type bitmap has all the type except for the TLS-A. Again, when the client asks for S-MIME-A, we can see that the type bitmap is again huge, but it has flipped a bit for S-MIME-A, which is not present, and the TLS-A is there even though it wasn't there in the previous query. This type is fine in a sense that it doesn't break anything, it works. The clear disadvantage is that it doesn't allow any aggressive use of cache, because from this proof of non-existence, there is no way how the resolver can synthesize anything useful. So it just, clutters cache and that's it. But it works. It doesn't break anything. Next slide, please. Matt, could you advance slide, please? Maybe you are trying. Okay. The problems start when someone takes a shortcut and uses a type bitmap which doesn't contain all the types which are present. The Cloudflare is sending all the types which are present plus some types which are not actually there, which is not a problem. Here we have the subset of types, so the type bitmap is not listing all the types. So for example, the client is asking for quad A, and the answer coming back has proof of non-existence which doesn't list A and quad A. So neither A nor quad A should exist according to this proof of non-existence. The problem is that when the client asks directly for A, the authoritative server will actually return a record and corresponding RRSEC. So imagine that we are a resolver and the client is doing happy A balls and sends 2 queries in parallel, one for quad A and the other one for 1A. And now, for some reason, the resolver decides to resolve the quad A first, and it gets this proof of non-existence. That proof of non-existence gets put into the resolver's cache, and then the resolver moves on to resolve the A query. But the data is already in the cache, so the resolver happily synthesizes no data answer, and obviously the site will be unavailable because I'm pretty sure that the domain owner didn't intend to send no data for A's. So, next slide, please. We can see that this is one type of breakage where this incomplete type bitmap breaks the aggressive cache, but also it's kind of hidden security vulnerability because it practically allows an attacker to take the broken bitmap or complete, proof of non-existence, including the broken bitmap, and replay it in an answer to a query, which would otherwise result it in a proper answer, including the data in OARCIC. So yeah, it's just broken, so we need to fix it. The question is how broken it is. Next slide, please. To measure that, we have taken Trenko dataset, which has 1 million of domains ranked from top to the bottom according to their popularity, whatever it is. Then we ran a scan looking for signed domains. So from this dataset of 1 million domains, we found like 35,500 domains which are signed. Next slide, please. And then with this list of signed domains, we ran DNSViz on all of them. DNSViz in the very recent versions have a check which explicitly queries for supposedly non-existing types and the types which are listed in the NSEC type bitmap and checks whether there are any discrepancies. So DNSViz was reporting 187 broken domains in our dataset, which is roughly 0.5% of signed domains, which is, well, could be better, but it's not a huge practical problem in terms of counts of broken domains if you look at the big picture, because it's like in practice it's less than 1 out of 5,000 domains overall in the dataset, so it's not really a common problem. Of course, domains are not made equal, so if the problem was affecting Google or Facebook, it would be fire. Everything would be on fire, but Trenko gives us the ranking for every single domain name in it. And we can see that the first domain with this type of problem has a rank 1005, so it's not like site everyone goes every day. And it was some US government website. Well, next slide, please.
Petr, you have 2 minutes remaining until Q&A time.
Yeah, that's fine, thanks. If we break down the breakage by NSEC and NSEC3, we can see that it's quite different. And the next slide, please, will show us why. The reason is that for NSEC, the breakage is concentrated with 4 operators, and each operator had a little bit different type of breakage. So that hints that they are using custom code, which didn't get the corner cases correct. And I have to say that the NIC BR fixed the problem in 2 hours since reporting it. So that's like super impressive. The other 3 were alerted, and we'll see what happens. Next slide, please. For NSEC3, the landscape is very different because there is no clear clustering by operator. The only larger cluster of domains is US Treasury, but all the rest is like little breakage here and there. And we can speculate why. I believe that's because this type of breakage is caused by an appliance or possibly more appliances. And my bet would be that it's the old F5 bug, which is like more than 2 years old, but either people didn't upgrade or didn't configure the appliance correctly after the upgrade, because the so-called fix from F5 actually requires manual configuration to generate proper bitmaps. Next slide, please. So to conclude, the next version of Bind will enable aggressive use of cache. And there is just a couple domains which are broken, but these domains will be hit even harder when we release. So please fix your domains. And I'm happy to accept questions if we still have time for them.
All right, thank you, Peter. Any questions can be asked by the Q&A tab and/or raising your hand if you'd like to ask the question in person. And you should see a survey pop up shortly that you can rate this talk. All right, our first question is from Pieter Lexis. You say for NSEC, will NSEC 3 be supported later?
That's a good question. Yes, the next upcoming major version will enable NSEC in like 1.4.2 or something. and the NSEC 3 will be in pipeline, but that's not going to be in the 0.0 release.
All right, last call for questions for Peter. Oh, there we go. Sam Weiler asks, did you find the breakage at Route 53 that Slack reported yesterday?
Funnily enough, this lightning talk is a coincidence of me doing the research, not for OARC, but for our purposes. And the test was running yesterday, and reportedly Route 53 already fixed the problem, and I didn't see it. So seems fixed.
All right, I am seeing no hands raised, and oh, we got a raised hand. All right, Ulrich Visser, if you would like to unmute yourself and ask a question.
Yeah, hi. Sorry for being so late here. Peter, I wanted to ask if I want to test my own domains, if they're doing well, what do I have to do to run the DNSViz? Because I don't think it shows up on the web of DNSViz, does it?
Well, on the web, you have to click through the options, and there is a checkbox like denial of existence, and you have to click on it and enable it explicitly, and then it will show up on the web. But I was using the command line interface, so yeah.
Thank you.
And the command for the command line interface is in the slide, so anyone who wants to scan larger list can use this.
All right, well, thank you very much, Peter, for your presentation. We will move on to our next lightning talk. This will be Brian Summers from OpenDNSSEC Cisco Umbrella, who will be presenting Bringing Up DOE. Brian, if you'd like to share your slides.
Okay, thank you. Yep, so I'm Brian Summers from OpenDNS, which is owned by Cisco these days. And I'm going to talk about our efforts to bring up a DOE service on our resolver infrastructure. Next slide, please. So we took the kind of slow approach by starting with proxy. We brought this up around the start of 2020. And the proxy was reasonably straightforward to set up. It was a Python program, essentially, that punts queries to the back end, adds a little special EDNS to say who was talking to us, which was interestingly talked about earlier in the proxy presentation. Adds a little special EDNS to tell the resolver who's talking to us so that it can treat them as special if it needs to treat them as special. As you probably know, our service does all sorts of filtering as well for clients. And of course, the proxy does all of the UDP truncation TCP querying. So ultimately, the TCP client on the front of the proxy will just get responses over TCP regardless of any packet sizes. So that kind of ran for, I guess, the best part of a year and a half. It was a problem for us as people started using DOE more and more. It used up more and more resources, and the number of resources that it used per query was quite startling. So next slide, please. So around about the end of 2000, start of 2001, we decided, okay, we need some native support here in the resolver. There's too many queries, too much infrastructure being used. So we looked at what was actually involved. And I thought it was fairly exciting that we could detect TLS connections on port 443. We already listen on port 443 because we do DNS crypt over that port. So we had to have a way of supporting DNS crypt and TLS sessions for DOE on the same port. It was reasonably straightforward, so we thought, okay, we're off to the races to do this. So we've got a few kind of things to deal with. The first was out of order TCP pipelining. Having an operating system make a TCP connection to our resolvers and then try to query things through that TCP connection kind of requires out of order TCP pipelining. If that doesn't work, then all bets are off. There's no point in using TCP if everything's serialized. as soon as you bump into a non-responding upstream name server, you're in trouble because all of the queries are going to pile up behind it. TCP pipelining was difficult. We had lots of camel problems trying to get this running. The camel problems were most viciously around when you have one client connected via TCP, they've got two queries to the same thing upstream, and those two queries are queued one behind the other. So both are waiting for the same response from upstream. And then the response from upstream times out, and we fail to respond because something else goes wrong. And you end up with a teardown scenario where a query tears down another query, which tears down the first query, and you can get yourself into a little bit of trouble that way. So there's lots of confusion in the internals of the resolver to get out of order TCP pipelining working. Then I guess the next step was the whole protocol there. So HTTP1 is easy, and you just read a bunch of headers and then go find the query in those headers, whether it's a GET request or a POST request. So my first implementation was just using HTTP1 because HTTP2 looked much harder. So I implemented DOE using HTTP1 initially. Fairly straightforward. HTTP2 is a binary protocol, as I'm sure many people know. We ended up using NG-HTTP2, which is a library that's available that Nginx uses. I guess that's where it gets the NG from. And this kind of fit reasonably well into the resolver and our use of the TLS layer. And of course, that was the big awkwardness in getting all of this stuff to work, was the TLS layer itself. And we had to deal with ciphers and protocols. It turns out that some ciphers are bad, some ciphers are good. Some protocols like old SSL2 and things like that are bad. And you have to use TLS 1.2, 1.3. So there was a little bit of a quagmire there, but working for Cisco, they already had a ton of requirements around this. So they basically spelled out exactly what ciphers and protocols we're allowed to use. So that was reasonably straightforward once I got my head around exactly how to program the OpenSSL layer with this. Big surprises came when I saw how OpenSSL buffering works. You can't just get a SSL thing and do reads and writes to it. When you do a read of 2 bytes and then do a read of whatever that size is, well, actually that's a dot thing. But when you do a read in OpenSSL, you can get 512 bytes, and actually it's read 10K in the background. And if you don't go back to the SSL layer and say, hey, have you got any more data in your buffer, then go trying to select on a file descriptor, you'll be disappointed because that file descriptor may never wake up. So there were lots of issues around understanding exactly what OpenSSL was doing on the buffering layer, and making sure that we dealt with that. And of course, certificate management was a little bit awkward, but I mean, we all know how to deal with certificates, so it was reasonably straightforward. And there are caveats to that reasonably straightforward that I'm bumping into now, but that's for another talk. And then right at the last knockings, we bumped into 2 other things. One was DDR. Microsoft and Apple are looking at ways of discovering equivalent resolvers that can do encryption. And they're basically working with things like these SVCB records that publish alternate interfaces to the same service. So we had to support SVCB records and HTTPS records, which are the same thing really, which was a last minute thing that we found out we had to do. And then one other kind of nasty, rotten HTTP technology is OCSP. OCSP is a way of stapling an answer to your TLS negotiation, or a piece of data to your TLS negotiation that says, and by the way, here's some signed proof that I haven't been revoked. And this is necessary because if at the operating system layer you're connecting to a DOS service, and you don't yet have DNS, then you can't go and look up revocation lists because you don't yet have DNS. So you need the resolver to be able to prove that they haven't been revoked or that they haven't been revoked within a given time period. Next slide, please. So, of course, once we got all of this in place, the rollout, which was something that I was kind of expecting to provide lots and lots of problems, it didn't. Once we actually got our resolvers up and running and accepting DO connections, we wanted to take over the proxy addresses. We had 4 Anycast proxy addresses, and it just went completely smoothly. We brought resolver listeners up in all of the data centers that we didn't already have proxies in, and that just worked. And then we went through an iterative kind of day-by-day process where we took down 3 data centers, took proxies down in 3 data centers, and then brought resolvers up in those 3 data centers for the proxy addresses. And it just worked. So it was a great success story at the end, but of course there was a whole bunch of failures in development. And again, this is a lightning talk, so you don't get to know much about the failures. So yeah, that's about all I've got. I'm happy to answer any questions.
All right, everyone, you should see a survey pop up shortly to rate this poll. And if you have any questions, please do so in the Q&A tab and or by raising your hand if you would like to ask it verbally. I guess my question while we're waiting, Brian, you mentioned certificate management in particular being on the annoying side. Is there one piece of it in particular or a recurring problem that you've seen that you'd like to advise us all about?
Yeah, I guess there's awkwardness because of the way I ended up doing it. So there are 3 kind of pieces of certificate. There's the key, there's the cert, and then there's this OCSP data. And the reason the OCSP data is part of the certificate is because when we distribute data to our resolvers, we want the same data to be on all of the resolvers. There's lots and lots of resolvers around the world. So we distribute the OCSP data, but of course the OCSP data is based upon the certificate, and the certificate is based upon the key. So if we want to change the certificate, well, so the mistake I made was the OCSP data is generated by a AWS Lambda, because that was just the easy way to do it. The cert is configured manually and pushed via our Stratus system, and the key is held in AWS Secrets Manager. So they all come from 3 different places. So it's easy to update the OCSP data, which is our automated job. But once we have a cert to update, well, now we have to kind of glue that with some new OCSP data so that they're introduced at the same time. And if the key changes at the same time, they all have to change at the same time, but they all come from different places. So I need to sort that out and have it so that when they need to come from different places, they're all consolidated and placed in one place at one time so that it all works.
All right, I'm not seeing any other questions, so I will thank you very much, Brian, for your presentation. And again, on behalf of the entire program committee, I'd like to thank everyone, our speakers and our attendees. And with that, I will hand things back to Keith Mitchell. Keith.
Okay, thank you very much, Jake. Great workshop. Thank you, everybody. That just went so smoothly, and there was some really good content and interaction. Before we finish for today, I just want to run through a few wrap-up points. First of all, what are we doing about next workshops? Well, before we think about the next workshops, we'd love to get your feedback on this workshop. So there's the survey link. Please, if you haven't already, there's your chance to give general feedback on meeting logistics and format and such like. The priority for our meetings throughout 2021, where we decided to do everything fully online, and we'll be adhering to that principle throughout next year and for as long as it takes, is that we want everybody to be able to participate, and we want everybody able to participate safely. So for 2022, we're going to start doing hybrid events. Obviously, this is all subject to pandemic conditions and whatever Omicron does to us all. We will see, but we want to try doing some hybrid events. And where events have an in-person element, then there will be pandemic precautions to protect attendees. We have some ideas what we want to do about that and a little bit of experience from other organizations, but we would very much like your feedback on the meeting format, meeting duration, meeting frequency, and in particular the safety items. I think that we did a couple of short online workshops in 2020 and one this year, and I think that we may continue with that format from time to time, whatever the conditions are. But that's the overall sort of big picture plan. In terms of specifics, we are planning and hope that we will do OARC 37 in Austin, in Texas, in February 2022, co-located with Nanogate 84, which has always been the plan. And the idea is that this will be our first physical virtual hybrid event. As I said yesterday, Dinesh and I will be doing a site visit there next week, and we hope to come back with much more concrete ideas about what is feasible, what's safe, and what we'll be able to do there. So while we digest that and the board makes some decisions, the CFP, the registration of the pandemic precautions will all be published and announced no later than early January. As I said yesterday, hopefully the plan is that OARC 38 will be in May, co-locating with the ICANN IDS workshop, getting back to that. We very much hope that we will be co-locating OARC 39 with RIPE 85 and Center Tech in Europe in the fall of 2022. So that's looking forward. I think, the final thing to do is just to thank everybody that made this workshop possible, in particular, VeriSign as a sponsor, both for this workshop and throughout the year. All the OARC members and supporters whose support has been solid for OARC for a very long time now. The program committee, who have put a great program together, and they haven't just put a great program together from a content point of view, they've been actively helping out with the various logistics of the meeting and the rehearsals. Special shout out to Maurizio as a crew member who has once again done all our social media postings today and yesterday. I'd like to thank Ulrich and Jake as the session chairs today, and Brett and Willem as the timekeepers. Thank you all for your feedback in the polls. We've got good response to that, which will give good data for the program committee going forward. Special mention to our outgoing program committee members. Jan for his 3 years on the program committee and everything he's done for this workshop, and for his contribution and service as the PC chair for the past year. Jake for his past 3 years of service on the PC, and Brett for his past year of service. So thank you to all of them. And that is basically it. I mean, there are lots of, and sorry, I forgot to thank our speakers, without whom we would not have these meetings. Just because we're not dragging them around the world on their own expense tab to have a meeting doesn't mean that they don't do extra work in terms of rehearsals and preparation for the online. So thank you. I really with some great talks this time. So thank you to all our speakers. And as I say, there are other ways that you can support OARC events, via sponsorship or patronage for a year, or indeed as a donation. So that covers OARC 36. Thank you all very much, and I look forward to seeing at least some of you in person for OARC 37. Have a great holiday season, and take care.
you.